Good morning, everyone. Welcome to today's hearing. Today we're going to hear further evidence from Professor Bisby.
Yes, Mr. Chairman, good morning. Good morning, members of the panel. I now call back, please, Professor Bisby.
Good morning, Professor. I think I left your status as a witness slightly uncertain on Thursday, so just to make things clear, would you mind making the affirmation again, please?
Sure.
Thank you. There are, the words are on the screen for you.
I do solemnly, sincerely, and truly declare and affirm that the evidence I shall give shall be the truth, the whole truth, and nothing but the truth.
Thank you very much. Now please sit down and make yourself comfortable. Yes,
Mr. Chairman, thank you. Professor, welcome back. We are going to hear your evidence today in response to questions that I have for you. We will take scheduled breaks in the normal way, as we have throughout the inquiry with the witnesses. Can I just ask you, please, one thing that I always ask all witnesses, and that is to keep your voice up, to speak slowly and clearly so that the transcriber who sits over there to your right can get down everything you say on the transcript clearly.
Sure.
Now, you've produced 6 reports for phase 2 of the inquiry, 3 of which we referred to last week when you gave your presentation, and those dealt with the experimental work that you carried out. So that was work package 1 and work package 2. Those were respectively LBYWP 1702 and LBYWP 2701. respectively, dated respectively 15th of March 2020 and the 15th of December 2021. And I'll call each of those the Work Package 1 report and the Work Package 2 report. Now, the third report that you produced to the inquiry when you gave evidence last week was your materials testing report at LBYMT 702 of the 24th of February 2019, updated on the 1st of June 2020. And that, as I think you told us, is to be read in conjunction with your final phase 1 report, 21st of October 2018, and that is to be found at LBYS 601. In addition, you've produced to the inquiry another report, and that is at LBYP 2601. Can we please have that up on the screen? And we can see that that is the Work Package 2 systems interaction reports. And here on the screen now is Phase 2 regulatory testing and the path to Grenfell, dated the 10th of November 2021, updated twice, 4th December 2021 and 1st June 2022 this year. And we'll call that your path to Grenfell report. And if we can go, please, to page 12 of that report, you'll see paragraph 1.16 under the heading Statements. And there again are the familiar fourfold paragraphs setting out a number of matters which cover the statement. First, are these your statements in relation to this report?
They are.
And secondly, you can see a signature at the bottom next to the date of the 10th of November 2021. Is that your signature?
Yes, it is.
Have you read this report recently?
I have.
Can you confirm that the facts and the factual matters set out in it are true to the best of your knowledge and belief?
Yes.
And can you confirm that the opinions you give are your honestly held professional opinions?
Yes.
And is it true that you provided your expert opinion in this report to the inquiry in the same way as you would have provided it to an English court?
That's correct, yes.
Can we then turn to another report, which is LBYP 2603? And this is entitled Phase 2 BRE Reconstruction Report. And there's a signature there above the 10th of May 2022. Is that your signature?
Yes, it is.
And can we go, please, to page 4, where we can see paragraph 1.1, and there again the fourfold statements about the report and a signature at the bottom next to the date. Again, is that your signature?
Yes, it is.
And are these your statements about this report in particular?
They are.
And have you read this report recently?
I have.
And can you confirm that the facts and the matters set out in this report are true to the best of your knowledge and belief?
Yes.
And can you confirm also that the opinions that you give in this report are your honestly held professional opinions?
Yes.
And also that you provided your expert opinion in this report to the inquiry in the same way as you would have done providing it to an English court.
That's correct.
Right. Now, lastly then, please, if we can turn to LBYP2 604, we can see a report entitled Phase 2 BR135 Desktop Assessment Report. And there's a signature there above the date of the 30th of May 2022. Is that your signature?
Yes, it is.
Can we turn, please, to page 7 in that report? Paragraph 1.2, the 4 paragraphs we can see there again above a signature against the date 30th of May 2022. Is that your signature?
Yes, it is.
And are these statements here statements that apply to this report?
Yes,
And have you read this report recently?
I have.
And can you confirm again that the facts and matters set out in this report are true to the best of your knowledge and belief?
I can.
And can you confirm that the opinions that you give in it are your honestly held professional opinions?
Yes.
And is it true that you provided your expert opinion in this report in the same way as you would have provided it to an English court?
That's correct.
And can you confirm in relation to all of these opinions that I've shown you this morning that your opinions and conclusions in them have not changed since they were produced to the inquiry?
That's correct.
Now, you've given evidence before, including in relation to your experience and your fields of expertise, and you've set those out in a CV that you provided in your final experts report for Phase 1 at Appendix E. And I'll just push that up on the screen so that those who want to look at that can. It's at LBYS 601. That's the final experts report. If people want to see, well, perhaps we should go to your path to Grenfell point, report at LBYP2 601, page 10. LBYP2 601, page 10. And here you, the paragraph 39 under paragraph 1.4, you summarise what you've already told us in the previous report I put up on the screen. And that runs over to page 11. And what I want to do is just summarise briefly with you what you say about yourself. First, is it correct you are currently Professor of Fire and Structures within the School of Engineering at Edinburgh University?
That's correct.
And also within the same school, the head of the Research Institute for Research and Environment.
Infrastructure and environment, yes.
Infrastructure and environment. And I think formerly you were Royal Academy of Engineering Research Chair.
That's correct.
As well as ARUP Chair.
They were linked, but
They
yes.
were linked. And in the UK, you are a chartered structural engineer.
Correct.
And in Canada, a licensed professional engineer.
That's right.
And also a fellow of the Institute of Fire Engineers.
Yes.
Institute of Structural Engineers.
Yes.
International Institute for FRP in Construction.
Yes.
And in Scotland, the Institute of Engineers.
That's correct.
Institution of Engineers. Yes. And I think you've advised various industrial and government research organisations in this country, as well as in the US, Canada, France, Switzerland, and Germany. Yes?
Correct, yes.
And that includes, or included, in relation to the development of design codes and guides internationally.
That's right.
And I think you are also currently co-editor-in-chief of the technical journal Fire Safety Journal.
Correct.
And is it right that your current fire safety and your structural fire engineering research is based on matters including building and infrastructure materials at elevated temperatures, fire-safe structural strengthening, and rehabilitation materials and fire performance of external cladding materials, products and systems?
Correct.
And I think you've published peer-reviewed articles in those areas, as well as in related areas, including sustainable building design and engineering education.
Correct.
And is it also correct, confirm for me please, that you've got extensive experience of engineering research, consultancy and university teaching, as well as the promotion of public understanding of science and engineering?
That's right.
Finally, I think it's right to say that, or let me ask you, you have received a number of awards for your commitment to high-quality engineering research and for your dedication to the broader academic and research communities.
Yes.
Yes. Let's then turn to your Phase 2 experimental work. Last week, we had the benefit of hearing from you on 9th of June a presentation to the inquiry on the experimental work that you carried out as set out in work packages 1 and 2, yes?
Yeah.
There was one matter which I think was an error, which I just want to pick up with you before we go on to some questions about work package 1 and 2. Can we please go to the transcript from last Thursday where you gave your presentation. That's day 289. And I just want to take you within that, please, to page 179. That's day 289, page 179. Thank you. And if we go to line 21, you say there, and you're describing the experiments where you remove foil faces from the insulation products. And if we pick it up at line 15, you say, of course we know that while there were exposed edges of insulation within the cladding system at Grenfell Tower, most of the insulation products, whether RS5000 or K15, had foil faces in place. In the case of the Kingspan product, again the foil facer is perforated. I therefore repeated the above experiments, but in each case I retained the foil on the front face of the insulation, including having foil on the front face of the combustible mineral wool insulation. Now, when you use the word combustible there, did you mean combustible mineral wool insulation?
No, I mean, I almost certainly will have meant to say non-combustible mineral wool insulation. Although, as I said during my evidence, any material that has a heat of combustion, strictly speaking, is not non-combustible. So it's the mineral wool is non-combustible from a regulatory perspective, but not necessarily from a physical perspective.
Yes, thank you. Now, I'd like to turn, please, to work package 1. And can we go to LBYWP 1702, page 5, paragraph 29. And there you say this: under the most severe heating conditions used in my experiments, I observed short-lived surface spread of flame over the polyester powder coating of samples of Renabond PE ACM. Are you able to say what the likelihood is that there was some surface spread of flame over the Renabond PE ACM in the early stages of the Grenfell Tower fire?
I mean, that's a very difficult question to answer. The footage that we assembled at phase 1 didn't show any obvious surface spread of flame over those panels in the early stages of the fire. As the fire grew, it's very hard to say where that spread of flame was occurring, whether it was a consequence of burning of the polyethylene core or a consequence of the powder coat. So, I mean, that's a very difficult question to answer. The amount of energy that would be liberated by any burning of the surface coating would be very, very small in comparative terms if you compare it to the amount of energy that can be liberated from the polyethylene core. So I wouldn't think, and I think I intimated as such in my report, I wouldn't think that that's a hugely significant observation.
Then if we look at the heading below that, it says alu-glazed window infill panels. Let's look at paragraph 33 there, still on page 5. You say, the alu-glazed window infill panels are comparatively easy to ignite, provided that even a small area of XPS foam is directly exposed to heating. This is due to the low thermal inertia of XPS foam. It is noteworthy that the low thermal inertia is also the reason that XPS foam is desirable as a thermal insulation in buildings. Now, given the conclusions that you've derived from your experiments in relation to the alu-glazed infill panels, are you able to reach any conclusions on the potential contribution of the ignition of the alu-glazed infill panels to the ignition of other elements of the facade?
Again, challenging to say definitively. I mean, the reason that comment is in there is because we have evidence from phase 1, from memory, that suggests that the extract fans that were located within small pieces of infill panel, essentially the same product, in the kitchen windows of the flats, flat 6s all the way up the building, that those extract fans softened and fell out quite early on in the fire. And certainly the footage that we have from the fire of the kitchen window of flat 16 early in the fire suggests that the extract fan had fallen out, and there, you can see a circular hole in that small panel of window infill panel material. If the extract fan falls out of that infill panel, then around the circumference of the hole where the fan was sitting, you will have had exposed XPS foam insulation. That foam insulation is quite likely to have both softened and melted and dripped and ignited and will have contributed to burning in that location and will have contributed to flaming that is likely to have impinged on the ACM. So that's quite a long-winded answer. But I think the answer is it's certainly possible that ignition and burning of the XPS core of the window infill panel that was holding the extract fan will have contributed to some extent.
And are you able to quantify that contribution?
No, not in any sort of meaningful way. You have a fire in the kitchen that is quite a well-developed fire and is venting flames out the window, and would have been regardless of the burning of the infill panel. So I would say some additional flaming, some additional energy release. Quantifying that, whether we're talking 1% or 10% or 20%, I wouldn't be able to say with confidence.
Moving on to Celotex RS5000, if we go to page 6 of this same report, please, you say this at paragraph 45. Furthermore, I have found that without, in italics, without its aluminium facer, Celotex RS5000 is comparatively very, in italics, very easy to ignite. The PR foam core of Celotex RS5000 has very low times to ignition, a direct consequence of its comparatively very low thermal inertia. If RS5000 had lost its aluminium facer, what is the likelihood, can you tell us, of the ignition of the PIR foam if it came into contact with downward flowing XPS?
So you have downward flowing XPS and you have Celotex RS5000 without a foil?
Yes.
I think it's going to ignite. Whether that ignition or the extent to which subsequent burning would be sustained is a more challenging question. But I think this PIR insulation without a foil facer, when it's exposed to a heat flux of more than something in the range of 25 to 30 kilowatts per square meter, for any appreciable amount of time, it ignites very quickly, as we saw in my work package 1 experiments.
So do we take from that answer that the relevant heat flux to make XPS drip and flow would be enough to ignite unfaced RS5000?
Again, it would depend on the duration, so it's not necessarily just the magnitude of the heat flux, but I think if you've got burning, dripping, flowing XPS, then you probably have enough heating to ignite Celotex without a foil facer, yes.
And what is the likelihood, and this I think flows from, as it were, from the last answer, but what is the likelihood of downward flowing flaming XPS coming into contact with non-faced RS5000 in the geometry at Grenfell?
I don't think that likelihood is very high, if I'm being honest. I would have to think quite hard about the configuration, which I don't have in front of me, the configuration of the the alu-glaze window infill panels at Grenfell Tower sat within a system of aluminium rails that made up the window assembly. So you essentially have an aluminium framing around those infill panels. So getting the XPS out of the window infill panels, notwithstanding my comments about the small panels that house the kitchen extract fans, there has to be a route for the XPS to get out, if you like, of the aluminium framing. You've got 2 aluminium sheets. The XPS between the 2 aluminium sheets would melt and start to flow and drip within the infill panel. As it gets to the bottom, it finds an aluminium frame. The extent to which it can come out of that frame will depend on a whole host of factors. And then if it comes out of that frame, where it goes, I think you'd have to look very closely at that interface between the aluminium framing and the cladding below the windows. From memory, I think I probably would consider that reasonably unlikely. I think it would more likely if the ACM cladding were still in place beneath the window. I think I would consider it more likely that XPS, the melted dripping XPS, would flow over the outside surface of the ACM, from memory.
And therefore not come into contact with RS5000, whether foil-faced or not foil-faced at that point?
I mean, eventually, probably yes, given that the ACM is probably going to ignite and burn quite vigorously and disappear. And eventually, yes, you're going to find some insulation there. And certainly below the windows, the way the Celotex insulation was cut and formed within the cladding cassettes below the windows, again, from memory, the top edges of the insulation panels, if you like, did not have foil facers on them. You know, they were cut to an angle so that you get a sort of a downslope on the ACM panel below the window. So if the ACM were removed, then you do have exposed Celotex at that location beneath the window. But it becomes a question of, whether we're in an upward fire spread mode or a downward mode or a lateral or horizontal kind of mode.
If we turn, please, to page 7 of this same report and go, please, to paragraph 49, you say there, from my experiments to date, it appears that flat samples of Celotex RS5000 tested in isolation do not significantly spread flame horizontally, in italics, in the absence of an applied external heat flux. Additional experimentation is required to confirm this. What additional experiments would be required to confirm that, in your opinion?
I would want to do a lateral ignition and flame spread type testing, both with and without the foil facer. So it would be similar. You could do something similar to a BS476 Part 7 lateral flame spread test. Yeah. I mean, I have to say, based on our experiments, what I expect you would see is that they would not spread flame very enthusiastically at all. Yeah.
And in the fire at Grenfell, would the RS5000 have been the subject of an applied external heat flux?
Can you repeat the question?
Yes, would the RS5000 have been the subject of an applied external heat flux?
Again, it depends on whether we're talking about, it depends on where the insulation is on the building, obviously, but I mean, yes, if you have a large external fire burning, then you have a large heat flux.
Yeah.
Yeah.
And the source of that heat flux would have been what, in your view?
Early in the fire, it would have been burning polyethylene from the ACM. I mean, very early in the fire, as we're talking about the fire getting from the kitchen out into the insulation, out into the cladding system itself, that source of heat flux could have been the kitchen fire itself. I talked last week about the potential route of fire spread through the side of the window, and in that situation, the kitchen fire would have provided the heat flux. As the fire grows, you've got most of the heat release, as I said last week, is probably coming from the polyethylene from the ACM. So in an upward fire spread mode, you're likely going to get the heat flux coming from that fire plume. As the fire reaches the crown, starts to go around the crown, and you have dripping polyethylene down the building, then it gets slightly more complicated in terms of where do you have polyethylene collecting, pooling, generating pool fires, igniting other materials, etc. At that point, it gets complicated, probably beyond the point that I could say for sure. Although in every case, as I've said, in every case, my view is that the ACM, PE, and the polyethylene, the burning of the polyethylene is what's contributing the vast majority of that heat flux. Now, I should also say that, of course, as the fire spread past flats in Grenfell Tower, either up, across, or down the tower, it typically ignited fires within the flats, and those fires then burned as, typical, if you like, compartment fires, ventilation-limited compartment fires, and you have fire plumes coming out the window for extended durations of time, given that the fire service couldn't do anything about those fires. So then you have a very significant external heat flux coming from the fire plumes generated by those fires over long periods of time. Now, those heat fluxes and those exposures of the cladding products are on time scales that are typically much longer than those that would be relevant to the external fire spread. So under those, I mean, it's actually quite an important point. After the fire, when we went to look at Grenfell Tower after the fire, and we did, a walk-around survey of the entire external surface of the building once the scaffolding had been put around the tower, and we examined the insulation, the extent to which the insulation boards had charred or been burned in the fire. The question is the charring and of the insulation that you observe when you walk around the fire after the days, weeks, months after the fire has been put out. To what extent is that charring evidence of charring that will have occurred as the fire was spreading, or to what extent is that charring that will have occurred as a consequence of the fires burning in the flats over long durations once the spreading had essentially occurred and the ACM PE was long gone? So that's quite a long-winded answer to your question, but I think it's important to think quite hard about the durations over which the materials and products that constituted the external wall arrangement, the durations over which their burning occurred, because products that release a lot of energy very quickly are much more hazardous from an external fire spread perspective than products that might contain similar amounts of energy but burn very, very slowly under different circumstances. And that's a very important distinction.
Yes, thank you. Sticking with page 7, can we look please at paragraph 51, where you say this: however, the ease of ignition of Celotex RS5000 may be relevant as regards initial growth of the fire outside the kitchen window, flat 16, where, without protection from foil facer or aluminium tape at a cut edge, it could have been one of the first or possibly the first cladding materials ignited, thus promoting ignition of other materials that were present at that location, for instance, the PE filler stroke core of the Reynobond PE ACM rain screen cassettes. Can you explain the mechanism by which the ignition of the RS5000 may have promoted the ignition of the PE filler, PE core of the Reynobond PE ACM?
Simply that if something ignites and starts to burn, then it's going to liberate energy. That energy is going to go somewhere, and if that energy goes, into the ACM, so to speak, heats the ACM and starts to mobilize polyethylene, which can then ignite, then that would be the mechanism. The mechanism is simply that burning of the insulation liberates energy that could then be used to heat the ACM and cause its burning.
And what about other elements of the facade?
There were other things in the cavity. You had the UPVC window frames, which would have been adjacent to that location, which can burn. You will have had EPDM rubber membrane around that location, which can also burn. You had, spray foam, bits of timber, various other things in the cladding system at that location. So there's a variety of things that could burn in that location, which is one of the reasons why I say, it's very hard to say with any certainty what was the first item ignited, and whether the first thing ignited would have continued burning in the absence of the other things is really difficult to unpick.
Are you able to quantify the amount of energy that the RS5000 would have allowed to be fed back to the other cladding components?
As I sit here, if we're talking specifically about the configuration that existed at Grenfell Tower, I think no is probably. I certainly wouldn't want to attempt it as I sit here. My work package 1 experiments do quantify the types of energy release or heat release that we would expect from the various insulation products, both with and without foil facers, under a range of heat flux conditions. And all of that work suggests that the energy contribution from the insulation products is quite small. And that's probably the best quantification I could give you, is comparatively quite small if you compare against something like the polyethylene from the ACM once it starts burning.
Right. Now, you say quite small. Do I take it from that you're not able to attribute a reasonably precise percentage?
This is something that I've discussed within my team at Edinburgh a lot. One of the challenges is, of course, we've performed experiments where we've quantified a number of things under a range of conditions. None of those conditions are exactly what was at Grenfell Tower. They are all representative of the physics, but we can't say for sure what was happening at Grenfell Tower in the cladding. It's one of the challenges when you go from the lab to reality. I was discussing this point within my team quite recently. because I expected I'd be asked this question. And the best I can say is that I think the contribution from the insulation in that initial environment and even to the upward fire spread is probably less than 10% of the overall contribution, something like that. It could be 2%, it could be 10%.
And before getting too hung up on figures, are you able to say, well, there are two things. First of all, flowing from that last answer, does the answer to the question I've just asked you depend on where in the building and at what point during the fire, treating it as a single entity, you are looking? I
think so, yes. Yeah, the work that I've done to date has focused pretty heavily on the upward, the fire going from a small fire to a big fire in an upward mode. How the fire goes from a small fire to a big fire in the lateral or the downward mode is more complicated. Yes.
Just pinning that down a little bit further, if I can. You use the expression going from a smaller fire to a bigger fire. Doing the best you can with a particular point, whether in timing or in quantitative terms, maybe that's the point at which the fire becomes out of control of any reasonable FRS, if that's a possible bridge point. But at that point, what would have been, up to that point, the contribution, in percentage terms, if you can, of the RS 5000?
Up to the point that the fire is, quote, out of control.
Yes.
And spreading quickly up the building.
Yes.
Less than 10%.
Right. And secondly, less than 10%, would you say that was negligible, or would you say that it was small but still materially contributive?
I guess it depends what we mean by contributive. I presume in your question that we're talking about the contribution of the insulation via its combustion, rather than the contribution of the insulation by its presence, if you like.
Yes.
Because as I explained last week when I gave my presentation, the fact that the insulation has a very low thermal inertia and is very insulating is critical, absolutely critical. So if there had been no insulation there whatsoever, whether Kingspan or Celotex or mineral wool, the outcome may have been quite different, significantly different, more than 10% different. No, the fact that insulating material is also contributing energy by its burning is what I'm referring to the 10%.
Yes.
So that's probably quite an important distinction for me to make.
And thank you for that clarification.
Yeah.
Then let's turn to your report dealing with Kingspan K15, page 9, please, paragraph 65. Page 9, same report, page 9, paragraph 65. And you say there, however, the ease of ignition of Kingspan K15 may be relevant as regards initial growth of the fire outside the kitchen window of flat 16 if it were present in this location, where, without protection from foil facer or aluminium taper to cut edge, it could have been one of the first cladding materials ignited, thus increasing the local heat flux and promoting ignition of other materials present. For instance, the PE filler stroke core of the Rainabond PE ACM rain screen cassettes. Are you able to describe for us the mechanism by which the ignition of the K15, as you say, could have promoted the ignition of the PE core of the Rainabond PE ACM as well as the other elements of the facade?
I would give the same answer I gave previously for Celotex, effectively. Yeah.
And when you say could have been, would you give the same answer in response to the question of quantification?
That's right. Yeah.
Yes. And if we go to page 26 of this report, please. Page 26, you say this at paragraph 165 at the top of the screen. Unlike polyethylene, both PIR and phenolic polymer foam are thermosetting polymers, i.e. they will char on heating rather than melting and dripping or flowing. As a consequence, it is the extent to which PIR and PF foam ignite and spread flame over their surface that is of primary interest, along with the extent to which they do or do not continue to contribute to heat release and flame spread over the timescales relevant to consideration of external fire spread during the Grenfell Tower fire. Now, given the absence of melting, dripping or flowing from PIR and phenolic polymer foams, what is the mechanism by which the PIR and phenolic foams contribute to the external fire spread?
By insulating the cladding system and making sure that the heat is retained within the system and fed back to the ACM, which exacerbates the burning of the ACM, and by liberating some admittedly small amount of energy via their own combustion, potentially by spreading flame, although I think the flame spread characteristics are probably not that significant, particularly if you had a foil facer in place.
Yes. Now, if we then turn to page 27, paragraph 169, you say, under the heading Products and Materials Under Investigation, paragraph 169, I decided, however, not to use the cladding products removed and retained from Grenfell Tower for my Phase 2 experimental programme. I made this decision because I felt that I would be unable to guarantee adequate control by others, either of the chain of custody for these products or the specific origin of the various samples, nor could I be completely certain that the products had not been damaged in some way due to their installation on the tower, their in-situ service experience, some exposure to heating during the fire, or mechanical damage during their removal. Do you consider that as a consequence of that decision that you've described there, you would have been unable to take account of any alterations or modifications to the cladding products which resulted from the manner in which they were installed, or the means by which they were affixed to the facade of the tower?
I mean, none of the experiments that I've performed intended or even tried to simulate or reproduce those issues in any way that I would say is directly applicable to Grenfell Tower. We were much more interested in understanding the mechanisms by which the different what the behaviors would be, and then the mechanisms by which those behaviors would manifest in the product. So no, I don't think I would agree with that statement.
Right, but focusing on the consequences of your decision not to use the cladding products removed and retained, did that materially, or should that materially affect the conclusions?
No.
So do we take it from that you didn't think it was necessary to take account of the exposure of the PE core resulting from the installation of the product in cassette form?
In the experiments that I performed, we did certain things to the ACM panels, certainly in the work package 2 experiment, that were intended to ask questions that were relevant to whether or not the panels were installed in a riveted form or a cassette form. So, for instance, as I showed in my presentation, we intentionally routed the rear face, the face of the ACM panel that was facing into the cavity, in our work package 2 experiments, because we recognized that the opening up, the separation, the removal of the inside aluminium face in a cassette configuration would probably drastically affect the burning behavior, and that's certainly something that we observed. We also performed, and I didn't present the results of these experiments last week, but we also performed some of the experiments that are presented in my work package 2 report, where we intentionally, if you like, overly routed or overly riveted the ACM panels. So we performed experiments where we looked at the time to escalation, the manner of failure, heat release rates, peak heat release, etc., where the ACM panel, in addition to being the baseline configuration that I showed during my presentation last week, we added, let's say, rivets to the ACM panel. So we intentionally secured the inside face of aluminium to the ACM panel so that we could see what the influence of that would be. And we did that actually in a number of configurations. So, we riveted the entire panel and observed what differences in behavior manifested in the experiment. So we riveted only the top half of the panel and left the bottom half free to open up. We did experiments where we intentionally routed horizontal lines over the aluminium face on the inside of the ACM panel to see what would happen if you had more exposed lines of ACM core and smaller aluminium inside surfaces that could mobilize in a different way. And we did observe differences in behavior. So, we've asked, in those experiments, I asked a number of questions that I think are relevant to understanding why the manner of fixing could matter, and I think have pretty clearly demonstrated, at least for myself, that the presence of rivets and routing it can be very important in terms of the timescales over which things occur.
Now, two things. First, I think you're drawing a distinction, which I may have blurred accidentally in my answer, between workmanship and in-use experience of the particular panels at Grenfell. And just to be clear, that's what you've excluded under 169 here. Is that right?
What I've excluded under 169, if you like, is the manufacturing and materiality of the products themselves. So the concern that I'm trying to express in 169 here is a concern that given that there was a very significant fire at Grenfell Tower, and given that that fire lasted for hours and hours, and given that there was a lot of downward mobilization of polyethylene in that fire, there were significant portions of the building, of the cladding system at Grenfell Tower that looked relatively undamaged, let's say. And the Metropolitan Police Service took all of those products, the undamaged products, and they put them in a warehouse. And they used those products for experiments so that they could understand, what products precisely had been used, what classifications they would achieve, et cetera, et cetera. The Metropolitan Police Service forensics team, working with BRE, did a whole host of things to try to understand those products. When it came time for us to perform the experiments related to my phase 2 work at Edinburgh, the question was whether we should ask the Metropolitan Police Service if we could have a substantial amount of materials that they had stored that had come off the tower, or whether we would be able to get from them a suitable volume of products that would allow us to undertake the work that we wanted to undertake, recognizing we were going to need quite a lot of each of the products in order to perform, the very large number of experiments that we ended up performing. So the two concerns were one, maybe that much product wasn't available via the MPS, given that they needed some of it for their purposes. And we certainly didn't want to deprive the MPS of the product that they would need in order to conduct, criminal work, et cetera. And so so where do we get the product from? And the answer is we get it from the corporate CPs to the inquiry. But of course, if one goes down that road, one has to be sure that what one is given by the corporate CPs is fairly representative of what was on the tower. So that's what I'm expressing there is, we recognize that probably we're going to have to go to the corporate CPs to get the products, and we wanted to have some confidence that what we were being given, hadn't been fiddled in any way. Let's put it that way.
Right.
Yeah.
But were you also seeking to eliminate error in your own methodology by using products which had actually been used as a result of...
Yeah, I mean, it's very, very difficult to know with certainty if any particular piece of cladding that we might obtain from the MPS was actually undamaged or had not been altered in some way, had not been heated in some way during the fire. But that was much more about the thermal history of the sample than it was about the manufacturing or installation history of the sample. Yeah.
And the second thing, just to draw out from what you've just been telling us, is that there's a distinction between non-use of the materials actually used at Grenfell Tower, which you've covered in paragraph 169, and what you've just said about that, on the one hand, and as it were, pre-designed installation or fixing methodologies, use of bolts or rivets on the one hand, or use of cassettes on the other, which were the subject of analysis by your team.
That's right, but not insofar as we were attempting to recreate the conditions at Grenfell Tower.
No.
We were simply attempting to understand.
Yes, and can you tell us, I know it's in your reports and your data, but can you summarise for us what you concluded as a result of the experiments done where rivets were applied?
That the presence of rivets substantially, and obviously with all sorts of caveats about how many rivets and where and of what type, et cetera, but if one manages by any mechanism in one's installation of ACM PE panels to prevent the aluminium skins from opening up, either with rivets or with framing or bracketing, or I'm aware that over the years in standardized testing of ACM products, sometimes little U-sections of metal were put around the edge of panels to try to keep the faces together. That will improve performance. Now that will, in our experiments, what that tended to do was to make it take longer for escalation to full involvement of the ACM to occur. But you still do get, eventually, full involvement of the ACM, and you still do get approximately the same total amount of energy release. So the presence of rivets, or the presence of any mechanism that holds the aluminium skins together, what it does is it prolongs the time until things go really bad, until you get a lot of burning and you get this rapid escalation. And that's, for me, very relevant to a number of questions and pieces of evidence that the inquiry has heard. The fact that riveted systems are apparently able to achieve a Class B result in the Euro classification system when tested in an SBI, but a cassette system does much worse. What's interesting about that is that if you let an SBI test run with a riveted system, my expectation is that eventually you would see the same result. It's just that you because of the timescales that are involved, you don't necessarily push the panels to that point. Again, within my team, my colleagues will hate that I use this terminology because we argued about it quite a lot as we were doing the work. But I started referring to these ACM products as tipping point products, and so there's a moment where things go from not so bad to really bad. And if you pass that point, all bets are off. And if you don't, then things can sometimes look like they're not quite as bad as they might be a minute later. And that's one of the reasons these products are so dangerous, is because they display this very volatile behavior.
Yes. Thank you. Now, moving on to page 32 of your report, you explain there in various places, but let's pick it up at paragraph 184, that you're aware that the Celotex insulation boards used at Grenfell were, I think, typically produced on two different production lines. This is para 183 for the Hipchin and the Hennecker lines. And at 184 you say this: Celotex via Linklaters LLP have provided the inquiry with a detailed account of these differences. I've not been able to quantify the possible influences of these differences on the reaction of these two thicknesses of Celotex RS5000 products to heating, aside from a brief comparative evaluation of the response of the RS5080 and RS5100 products supplied to me. This comparison is presented in section 8.7.3. I do not, however, consider it likely that the temporal variation in manufacturing inputs/processes is significant. What do you mean there by temporal variation?
So I mean, I'm not a polymers chemist, nor am I someone who manufactures polymer foams. But the base chemistry of these products didn't change a whole lot. It seemed to me in reviewing that information that there were little tweaks and changes and decisions made by the manufacturing operatives in terms of a little component here, little component there, probably based on things like the temperature in the facility that day, potentially ambient relative humidity and things like that might influence manufacturing. I don't know. So I mean, I would hesitate to put too much stock in that. If the inquiry feels that the changes in, let's say, chemical inputs to manufacturing process over time warrant investigation in terms of the possible outcomes for the resulting product, then I would probably insist that the inquiry ask a polymers manufacturing specialist rather than me.
But it's really the word temporal I was asking you.
Yeah, temporal. I just mean in time. If you look at the data that we were provided, again from memory, it was quite some time ago. I looked at this. There's little adjustments that are made to the manufacturing process in time.
Right.
And I felt that was probably unlikely to significantly alter the outcomes of what we would observe if we took a piece of the product and tested it in some way. It's not going to vary significantly any of the reaction to fire properties that we looked at, in my view. Heat of combustion, critical heat flux for ignition, those sorts of things. I wouldn't expect to see differences.
Yes, I see. Now, if we go then to page 58 of your report, please, let's look together at paragraphs 328 and then 330 on that page, under the heading Effects of Melting and Dripping. And at 328, you say this: in my Phase 1 final expert report, I've identified that melting and dripping of burning PE filler/core material from Rainabond PE ACM rain screen cladding cassettes played a critical role in both the horizontal and downward fire spread experienced during the Grenfell Tower fire. I've also identified that XPS foam insulation that formed the core material within the alu glaze window infill panels may have been a secondary source of melting and dripping thermoplastic polymer. And then at 330, you say, PIR and phenolic foam insulations, however, are thermosetting polymers which will not melt. Are you able to explain how your experiments in Work Package 1 or Work Package 2 quantify or measure the extent to which RS 5000 or K15 may have contributed to the downwards spread of flame?
In a direct way, the RS 5000, in a direct way, won't have contributed to the downward spread, in that the RS 5000 product itself isn't going to mobilize bits of itself downward. You're not going to get bits of burning PIR foam mobilizing downward and spreading flame by that mechanism. Obviously, the extent to which those products insulate a cladding cavity where you might have other things burning is going to be relevant to the downward mechanism, in that, if you have more heating locally, more melting of ACM, more mobilization of PE, you're going to get more downward. For the Celotex, as in terms of the material that made up the core itself, no direct involvement, although contributory involvement to the other mechanisms of downward, i.e. the melting of the polyethylene. With respect to the phenolic, I would say largely the same thing, with the small caveat that we did observe that the phenolic foam of the Kingspan product did have a tendency to spoil, to become mechanically detached from the face of the insulation when we didn't have a foil facer there, when there was no foil facer there to keep that material in place. So you would observe pieces of glowing phenolic foam that would detach and drop downward. That is a possible contribution to downward, although again, you're not talking a huge volume of material. These pieces of material, in the absence of an applied external heat flux, would go out very quickly. They wouldn't continue to flame. Right. So it's not a huge issue, but it is a small distinction between those two products that I think is relevant.
Right. So just to be clear, then, your findings were that RS 5000 would not produce burning, flaming debris of any kind, but Kingspan K15 would.
Although I would hesitate to say that Kingspan K15 would develop, a lot of burning, flaming debris. I would say that we observed bits of glowing phenolic foam that would detach from the face of the sample and then drop downward. Yes.
So it's a qualitative difference, but you can't really say much about the quantitative difference.
That's right.
Yes, I see.
Yeah.
Then, if we go, please, to. Let me just ask you that. Are you able to say, or comment on the extent to which melting PE may lead to the involvement of PIR or phenolic foam into the fire through pooling?
Significantly, yes.
Yes.
I think pooling of PE on surfaces within and outside the cladding was very significant at the Grenfell Tower fire.
Yes. Now, you showed us last week very helpfully your drip tray in the work package 2 experiments, when we saw that from the video in particular. Are you able to make any analysis or assessment for an experiment which was designed identically to your work package 2 experiments, but which replaced the drip tray you used there with an exposed edge of a sample of RS5000 or K15 or Rockwool?
You mean if instead of having a steel drip tray, we have a piece of insulation there?
Yes. So molten, burning polyethylene falling onto unexposed RS5000 or K15 or Rockwool.
No. I'm not able to say anything confidently about that. We certainly didn't do it. We certainly didn't try that to see what would happen. I suspect that in that scenario, you've got polyethylene dropping onto a very insulating surface. Unless you've got mineral wool where the polyethylene might actually, wick into the fibers, and I have absolutely no idea what would happen under those circumstances. But one of the things that's interesting about the drip tray that I didn't discuss last week is when we were developing the experimental program, as I mentioned last week, the reason we had the drip tray was because if you don't control, if you like, the pool fire that you get, the burning polyethylene pool fire that you get once the polyethylene starts to mobilize downward, you get polyethylene going all over the place, and you get a pool fire that is very hard to control the consistency of from experiment to experiment. So the drip tray was created or was placed in the rig so as to make sure that the pool fire we got was the same every time, and we could ask other questions that were perhaps more interesting in a more controlled way. When we were doing our initial experiments to kind of finalize the procedure that we were going to use in the exact setup, we ran experiments where we had the drip tray, but the drip tray wasn't. I didn't mention it again last week, but the drip tray, you have a steel ledge underneath the ACM. On top of the steel ledge, you have a drip tray. Between the drip tray and the steel ledge, we had a thin piece of ceramic paper, which is essentially an insulating ceramic paper, a couple of millimeters thick. When we ran an experiment without the ceramic paper, it didn't escalate. When we ran an experiment with the ceramic paper, it did escalate. Right. And so we always used the ceramic paper. Now, if we had left the burner in longer, various other questions we could have asked about the extent to which we needed an input of heat to make the experiments escalate. But that fact indicates that, or indicated that the extent to which the polyethylene in the pool fire was kept warm, was insulated itself as a pool fire, was relevant. So if you have the pool fire developing on a highly insulating surface, then probably it's going to make matters slightly worse.
Yes, thank you. Now, if we then go to paragraph 331 here, same page 58, you say melting and dripping of polymer filler/core materials can be expected to play significant roles in the responses to heating of both Rainabond PE-ACM and alu-glaze window infill panels, since they will influence the extent to which the thermoplastic filler/core materials burn in situ at the sample location, or rather in some other location once mobilized. Can you explain what you mean by since they will influence the extent to which the thermoplastic filler/core materials burn in situ at the sample location, or rather in some other location once mobilized? What do you mean by that?
I mean that it matters, I guess in simple terms, I mean that it matters where the energy goes. Or if the energy goes. So these materials, the polystyrene, the XPS, and the polyethylene, are quite calorific materials. They have high heats of combustion, and where and when that energy that's essentially locked up in the material is released matters. So if you have a lot of mobilization of the polyethylene, the polyethylene in the cladding is no longer where it started, and where it goes matters. So if if the polyethylene drips out of the cladding and into the atmosphere and falls through the sky and lands on the pavement at the base of the building, which we did see some of that, then the influence of that burning polyethylene on the cladding fire locally has been removed. If, however, the polyethylene drips and pools in the shelf at the bottom of a cladding cassette, these cladding cassettes on the tower, certainly the spandrel panels, you have the face of the panel comes down, it comes in above the window, and then there's a little lip up on the back of that cladding. You've got essentially a perfect container for a pool fire of polyethylene sitting in your cladding. So every spandrel cassette at Grenfell Tower is essentially a drip tray for burning polyethylene.
On the inside?
On the inside of the cassette, within the cladding system.
And therefore looking at the foil facing?
Looking at the insulation, that's right. Yeah, so you have a very efficient system for creating the worst possible fire in those cladding cassettes. You have a physical means by which to locally collect pool fires of burning polyethylene within your cladding, so that energy can be released locally in the worst possible way for upward spread. Yeah.
Now, can we go to page 81 of this report, please, and go to paragraph 422? You have set out some graphs on that page under figure 32, measuring heat release rates for typical samples of ACM. And at 422, you say this: the heat release rate is central to evaluating Yes, 422. The heat release rates from these small samples are comparatively low, you say. It is noteworthy that the measurement resolution of the HRR measurements made by the University of Edinburgh's furniture calorimeter is insufficient to provide high-fidelity data for such low heat release rates. However, this does not affect the conclusions drawn from the data. Then you go on to say, yes, I think it's probably enough for my question. Is it your opinion that a feedback loop existed during the fire at Grenfell Tower?
Yes. There's always a feedback loop when a fire grows. Yes.
Yes. And are you able to identify the elements of the facade which would have contributed or created this feedback loop?
Anything that had a heat of combustion will have contributed to some extent to that feedback loop.
Right. And what would that include? Can you identify the elements?
In order of decreasing relevance, I can try to do that. In order of decreasing relevance, the ACMPE, first and foremost, the insulation products, whether Celotex or Kingspan at any given location.
Yes.
And then all of it, really. Any timber that might have been there, UPVC window frames, window surround insulation, EPDM membrane, spray foam, anything that could burn will have contributed to some extent. However, very minor in some cases, but yeah.
And if we go back to page 77 and look at paragraph 411 next, you say there as follows: the heat release rate is central to evaluating fire hazards since it determines the amount of energy released from a material that is available to be transferred back to the fuel via convection and radiation, thereby creating a positive feedback loop and possibly resulting in fire growth and or spread. Now, the heat release rate that you've generated, does that come from all of the components or each one combined? Each one individually?
The heat release rate that one measures when one observes a fire is going to represent, typically, if you're measuring the way we did in the experiments in the lab at Edinburgh, what we're measuring is the total heat release rate that comes from everything that may be burning. So yes. Everything.
And when you say via convection and radiation, Are you describing there, and I don't want to put words in your mouth, but are you describing there the effect of heating when a pool fire in a drip tray on the, so to speak, on the inside of the cassette on Grenfell Tower, heats the insulation and creates rising heat, radiates but creates rising heat?
I mean, I think, which paragraph is that in again?
411.
I mean, yeah, I mean, I think 411 could be read almost without via convection and radiation. Those words are probably not necessary. The key idea in that paragraph is that when you have heat release, the heat release rate is telling you how much energy is being released per unit time. And the more energy you have, the more likely it is that that's going to feed back to the fuel and cause the fire to grow. The convection and radiation are just the specific heat transfer mechanisms by which that would occur.
Yes, I see.
Yeah.
And if we go on then to page 104 of this report and look at paragraph 606, you say there, 3/4 of the way down your screen after the reference to the video Bisby, you say, based on the experiments performed on 100 millimetres times 100 millimetre samples of Reynobond, PE, ACM and alu glaze, I would estimate that the majority of the polymer mass lost from samples incorporating thermoplastic filler stroke core materials, i.e. 50% or more of the polymer mass lost in all such experiments to date, was due to mobilization of these polymers downward, i.e. dripping or flowing. What would have been the effect of a downward dripping or flowing of the polymer?
Twofold. I mean, one, it would have removed energy from the local site of burning and taken that energy somewhere else. Where else depends where the polymer goes. And two, it's in the conditions that we observed, certainly for the ACM PE, that polymer is burning whilst going where it goes. And so if it lands somewhere else and it continues to burn, which it appears to have done, then that's a pretty effective downward fire spread mechanism. I mean, that's one of the reasons why at phase one I really focused in on the crown detail at Grenfell Tower. The upward fire spread mechanism is, pretty straightforward. The lateral, the horizontal fire spread mechanism at Grenfell Tower, which is quite unusual in terms of things we've observed in other cladding fires that involve these products, I believe is a direct consequence of the presence of the crown and the fact that the crown provided a mechanism by which the fire could go around the building. And then the downward spread from the crown is what effectively makes the fire go sideways. The diagonal lines of burning that you saw on Grenfell Tower in the fire, and those diagonal lines, how they progressed around the building, are simply a manifestation of the flowing of PE down from the top of the building, as opposed to, let's say, a classical lateral fire spread mode across the horizontal surface of a product.
So, yes, I follow. Are you able to quantify the contribution to the intensity or propagation rate of the fire of the downward flowing or dripping polymer from Reynobond, or perhaps also with the alu glaze? XPS.
Am I able to quantify it? No. Yeah. I mean, not in any useful way, I don't think. And I quantify with respect to what? I think that is the mechanism by which the fire goes down and around the building. I think in the absence of polyethylene, it simply doesn't occur. You just simply wouldn't get the downward and horizontal in the absence of the polyethylene.
And if we go, please, to page 111 of this report, paragraph 651, you say there, I felt it was important to satisfy myself experimentally that the ignition and physical straight mechanical deformations of Celotex RS5000 PIR and Kingspan K15 phenolic foam insulations were broadly similar to the cases where they were exposed to heating on a cut edge rather than on a flat face with the foil facer manually removed. What was the importance of demonstrating the ignition and physical stroke mechanical deformations of the RS5000 and K15, which you describe in this paragraph?
I wanted to make sure that what I felt from so earlier. This is the work package 1 experiment. So in the work package 1 experiments, as I discussed last week, we did experiments with and without foil facers, and we observed how the insulation products behaved under those circumstances. But those experiments were performed by taking sheets of insulation and essentially peeling off the aluminium facers. And so the surface of insulation that was exposed in those experiments was the front face of the foam panel with the aluminium removed. Now that is probably, but not definitively, the same situation as you have at a cut edge of the polymer foam, because of the way these products are manufactured, because for the Celotex RS5080 product, you have, as I mentioned at phase 1, you have in-depth glass fiber meshes that are sort of in the insulation in depth within the foam. And also when the aluminium foil facer is somehow adhered to the foam in a way that we've not interrogated in any way, so the peeling off may leave some residue of something there. So there's all sorts of reasons why, I wasn't, and we know that the locations in Grenfell Tower where we were concerned about the direct exposure of the polymer foam cores of the insulation products were situations where we had cut edges, not where people had intentionally removed the facers by peeling them off. So I just wanted to make sure that there was no substantive difference in the behavior under those edge exposure conditions, both because they were the ones that existed actually in the tower at Grenfell Tower, and because the peeling of the aluminium could potentially result in some differences in behavior, but we didn't observe anything that I thought was particularly different. So that work was really just confirmatory. I just wanted to make absolutely sure we weren't missing something.
Yes, I see. And if we go on the same page, please, to 657 at the bottom, you say, for Celotex RS5080, ignition occurs within 1 second of heating exposure and is followed by pyrolysis of the thermosetting PIR foam with continued minimal flaming. The overall response is sufficiently similar in appearance to this product's response when tested in a face-on heating condition without a foil facer that I do not consider additional characterization of edge exposure to be warranted. I consider that face-on exposure data to be broadly applicable to edge-on exposure. What is the significance to the intensity or propagation of the Grenfell Tower fire of the response of the RS5080, which you described there?
What those experiments showed was that under pretty severe heating conditions, that the behavior of the PIR foam core within the Celotex product, when you actually exposed the cut edge, was broadly the same as it was when we exposed the samples with the aluminium faces removed. So all of the conclusions that I drew with respect to the no foil RS5000 case in the work package 1 work are relevant. So easy to ignite, charring, reductions of heat release rates, eventual cracking, maybe a bit of ongoing combustion in the presence of an external heat flux, but pretty low heat release rates. All those sorts of things were equally relevant to the side exposure.
Right. And then, Mr. Chairman, finally on this topic, before we have the break, if I may, page 116, please, paragraph 680. You say there, based on my experimental work, I have concluded that in most cases the majority of the PE filler stroke core material is likely to have mobilized downward, i.e. dripped, during heating. This is likely to have been accompanied by flaming of the downwardly mobile material and the formation of pool fires where it was able to collect on horizontal surfaces both within and outside the rain screen cladding system. Now there, when you refer to downwardly mobile material, are you referring, just to be clear, to the burning, dripping, flowing polyethylene core material?
Yes, absolutely.
Yes. And what effect would that burning, dripping, flowing material have on the propagation of the fire?
It's going to spread it. It's going to grow the fire. It's going to spread the fire.
And pooling?
Yeah, I mean, pooling of polyethylene means you're going to have a local pool fire burning with significant heat release. That energy is going to go somewhere. If it heats ACM or insulation, it's going to contribute to combustion of those products, and you're going to have a bigger fire.
And in relation to the horizontal edges, you've described already very helpfully this morning the return internally into the cavity of the cassette with the lip that retains flowing, dripping, melting polyethylene. Are there any other horizontal areas within the cavity other than that return?
Yeah, I mean, that was with respect to the spandrel panels that I mentioned. That the column cassettes also have little returns on them, not quite as substantial as the spandrel cassettes. And indeed, at phase 1, I presented some images and some video evidence where you can actually see polyethylene burning in the cladding system, kind of between the cracks of the column cassettes. I think on those horizontal surfaces, you have pooling polyethylene. You can see flaming in those locations in cassettes that look otherwise intact. I mean, the other location, which sort of, ironically, given the purpose of cavity barriers, is on cavity barriers that will have been installed within the system. These cavity barriers kind of protrude horizontally out into the cladding cavity. They're made of a mineral wool insulation, and you could have polyethylene falling onto the cavity barriers within the cladding system, pooling there, burning locally, and making matters locally worse for the cladding system. Certainly for an upward fire spread mode. Yeah.
Yes, and that's internally. What about externally? Where would the horizontal surfaces be externally?
Well, you have window sills and various other locations such as that. There weren't on the outside of Grenfell Tower. There weren't actually a whole lot of horizontal surfaces on the outside of the cladding, if you like. Even the window sill areas were inclined downward as soon as you got outside the glazing. There was almost immediately a downward slope to the cladding cassette.
Yes. Well, thank you very much, Professor. Mr. Chairman, is now a convenient moment for the morning break?
Yes, I think it is. Thank you. Well, Professor Bisby, I think it's time we had our morning break, so we'll stop there. We'll resume, please, at 25 to 12. And you know the drill. Please don't talk to anyone about your evidence while you're out of the room.
Certainly. Thank you.
Thank you very much. Would you go with the usher, please? Thank you. 25 to 12. Would you ask Professor Bisby to come back in, please? Thank you. All right, Professor Bisby, are you ready to carry on?
I am.
Yes,
Thank you.
Yes, Mr. Millett?
Thank you very much, Mr. Chairman. Professor, can we now turn to Work Package 2 and the report, which we'll find at LBYWP 27001. And there it is. We looked at it very briefly earlier. It's dated the 15th of December 2021. And if we go, please, to page 5, paragraph 32, you say, the combustibility of the insulation product used has been shown to be of secondary or even tertiary importance based on our experiments when ACM PE rain screens are used. The combustibility of the insulation played an obvious role only when large surfaces were unprotected by foil faces and were thus able to support ignition and widespread surface flaming of the insulation. Does that mean that where foil faces were damaged or simply not present, such as on cut edges, the insulation did support ignition and widespread surface flaming?
Yeah, the data that would underpin that paragraph would be data where we looked at the amount of mass that was lost. So maybe I'll step a couple of steps back. So as I explained last week, when we performed these experiments, we had the ACM panel was mounted on a scale that sat on a load cell. And the insulation products were also mounted on a load cell so that we could measure the mass loss with time as the experiments progressed. That enabled us to, if you know how much mass is lost and you know what the heat of combustion of the thing that's burning is, you can, in approximate terms, figure out approximately how much energy might have been liberated by that mass loss, if you like. So you can sort of figure out what the contribution of the different products is to the burning by using mass loss as a proxy measure of energy release, if you like. And when we did that comparison and looked at the loss in mass up to the point of escalation to full involvement of the ACM, what we found that the mass loss from the insulation was only significant when its foil facer was removed, and that in some cases the amount of energy that would have been liberated using mass loss again as a proxy for energy release would have been about the same as was released from the ACM. So that's where that comes from. I don't know if that clarifies the point, clarifies the question at all.
Well, I was more interested, really, but thank you for that clarification anyway. But I was interested in the question of damage to foil facers. Let me try it slightly differently. Is it the case that your opinion is that let me try again. Do you think that once the exterior cladding is on fire, that damage to the foil facing is inevitable?
Once, I mean, if the ACM PE is burning, then the foil facer is going to be damaged and removed at some stage. Yes, I mean we saw that in our experiments. Yes. Once you had a significant amount of burning from the ACM PE, the foil facer was typically removed. You know, it would bubble and fray and melt and fall off. Yes.
So taking it step by step, does that tell us that at some point in the Grenfell Tower fire, the foil facer ceased to be a protective against significant mass loss?
Yeah.
And therefore began to contribute to the total energy overall.
That's right. I mean, yes, but again, when that happens in the process of escalation is quite important. So at that point, the ACM is already well away, yes, let's say, and burning quite well.
And in answer to that question, you say it's an important question. When did it happen, or does it happen in the escalation process?
When is the foil facer lost?
Yes. At what kind of point?
The foil facers, again, from memory, without watching all of the videos back, I wouldn't be able to say for sure, but from memory, it's in that region when the escalation occurs, either immediately preceding or as the escalation to full involvement of the PE occurs.
Now, we may be able to trace this through a little bit more. Can we go to paragraph 49 on page 9, please, in this report? You say there, the condition that leads to rapid and irreversible fire growth has been identified as the mechanical separation or otherwise compromising of the ACM's inner aluminium skin, which exposes a large area of polyethylene to the fire in the cavity. This results in a rapid increase in the energy release from the fire and promotes rapid fire growth. Is it the case that once the exterior cladding has attained irreversible fire growth, which you describe here, that will in turn cause the insulation to burn as well, provided it's combustible, regardless of whether it's foil-faced?
Yes. I mean, I think in a fire, never say never, but I think in a fire of that intensity, if you had an ACM PE rain screen burning adjacent to a foil-faced polymer foam insulation with a cavity, then that insulation is going to get involved in the fire. Definitely, yes.
And then if we turn to page 63, figure 17, we can see at the top of the page some photographs taken, or selections of photographs taken from experiment 21, and you can see the line burner there as the method of ignition. Do your experiments in work packages 1 or 2 quantify or measure horizontal flame spread from a single point of origin, as was observed at Grenfell?
No. I mean, I guess I might dispute horizontal flame spread from the point of origin as was observed at Grenfell, depending on what kind of horizontal mechanism we're talking about as well.
Fair enough. But, given the small-scale nature, though, of the experiments in work package 2 and the absence of a whole system test, what conclusion, if any, can you reasonably draw regarding the contribution of the insulation to the spread and the intensity of the fire which did occur at Grenfell?
That is a very important distinction, and something that's important to be clear about is that these experiments were focused on growth of a fire from a small fire to a large fire in an upward fire spread mode. The consequent spread of the fire around and down the building is not addressed by these experiments. It's very important to be clear on that. It's, one of the reasons why I labored the point a bit in the first session this morning to say, to explain sort of what my view of the lateral and the downward is associated with the burning of the polyethylene, rather than what we might call a classical horizontal or lateral fire spread over the surface of a product.
And if we go to page 121, paragraph 644, paragraph 121, 644 at the foot of the page says this, under the heading, Contribution of Insulation to Total Release of Energy. It says, the data presented in this figure are the total energy release that can be expected in cases where the cladding is allowed to burn without intervention until local burnout of the ACM, at which point the insulation also typically self-extinguishes, notwithstanding my previous comments regarding ongoing smouldering combustion of the Kingspan K15 insulation. What is local burnout of the ACM?
It's perhaps slightly imprecise words, but what I mean by that is essentially until the polyethylene's not burning anymore at the location of the fire that we're interested in. Yeah. So basically the polyethylene, there's no evidence of any further burning of polyethylene.
Whether within the panel or
in the drip tray, yeah.
Right. And in relation to the figures of contribution played by RS5000 and K15, of the total energy released until the end of the experiment. I think we probably need the figures for those. Can we go please to, first of all, figure 33 on page 78. Let's have that up first. You showed us this last week. And then again, perhaps have it side by side. Page 123, paragraphs 655 and 656. You can't quite. Yeah, that's it. We may have to scroll across. That's it. You give figures there of 20% and 53% up to as maximums, likely maximums in a worst case scenario for Celotex RS5000 in 655 and K15 in 656. Now, just taking that data and those opinions together, is it right that these experiments were terminated at 20 minutes?
Yes.
Now, what would have been the impact on your conclusions about the fire at Grenfell Tower, given that it went beyond 20 minutes?
It's an interesting question. At the end of the 20 minutes was chosen essentially arbitrarily because in many of the experiments, anything that was interesting that was going to happen had happened, or everything had gone out and there was no further combustion that we could observe from the rig beyond 20 minutes. So, all the burning had ceased, if you like. How that relates to the fire at Grenfell Tower, as I mentioned earlier, at Grenfell Tower, as the fire spread around the building, it ignited compartment fires, which then burned within the compartments for much longer durations. And so you had further thermal exposure to whatever products might have been left on the cladding due to the fire plumes, so insulation in particular. So any insulation that would have been left after the external fire had kind of spread away, gone away, the ACM was gone. That burning was able to continue because you had fire plumes coming out the windows as a consequence of the flats burning. Remind me of the question again, sorry.
Well, no, I can build on the answer, I think, which
Okay.
is, what was the basis of the assumption that, as you say in the last answer, that anything interesting that was going to happen had happened within the first 20 minutes?
Right. Yes. So yes, and I've remembered now where I was going with my answer. So in the case of experiments that involve the Celotex product, from memory, by 20 minutes, everything had gone out. There was no further combustion that was observable at all. In the case of some of the experiments with the Kingspan product, there was, as I mentioned last week, some ongoing smoldering of the insulation that occurred. Actually, in some cases, that continued up to 20 minutes. And at 20 minutes, we just sort of called it and said, OK, well, we're just going to stop at 20 minutes now. If we had let it run, whether that smoldering or the extent to which that smoldering would have continued beyond the end of the 20 minutes is anyone's guess. The intensity of smoldering tended to decrease with time, so one imagines that eventually it would stop. But we don't know. I mean, one of the things that was interesting about the experiments involving the Kingspan product, the K15 product, was that long after the ACM had burned away, and there was little evidence of any ongoing burning of the polyethylene, you still see this smoldering combustion ongoing, and you still and eventually, what actually happened is you get smoldering combustion essentially eats its way all the way to the back of the 100 millimeter thick Kingspan product, and you actually have smoldering combustion kind of coming out the back of the insulation panel in our rig. So that was something we didn't observe for the Celotex.
Right. And where would that, on Grenfell Tower itself, if that had happened, where would that heat have gone?
At Grenfell Tower, the insulation was butted up against the concrete of the building, so it would have gone, to the concrete, or would have been. I mean, it would have been slightly different because smoldering combustion depends on the availability of oxygen and the extent to which energy is retained within the insulation. I mean, to sort of highlight that point, one of the things that we observed that was interesting with respect to the smoldering was that the Kingspan products, when tested with the foil facer, seemed to smolder better, if you like, than when they were tested without the foil facer. And that's because some of the foil facer inevitably remains in place after some combustion and pyrolysis of the underlying polymer has started. And that foil facer kind of counterintuitively, once you have some smoldering in the foam behind the foil facer actually keeps heat in the smoldering foam and makes the smoldering worse. So in that respect, having the foil facer on the K15 product actually made the subsequent smoldering continue for longer than in the case where it wasn't there.
I see.
So it's sort of a counterintuitive result.
Well, it may not be counterintuitive. Would this be right, that it actually has a double effect? The presence of the foil facer protects the integrity and the combustion of the K15 for longer, but once there's combustion, but the foil facer remains in place in parts, it lasts longer.
Yeah, I mean, the foil keeps energy out, but it also keeps energy in.
Yes, that's an even better way of putting the duality.
Yeah.
Now, as you've said you used a 20-minute cut-off period. Just standing back and answering the question in very general terms, as we've seen, I think, throughout the inquiry, the testing regime has tests which have termination times. In general, what are those termination times based on? What assumptions are made generally about about a particular termination time?
I mean, typically our experiments were terminated, or we chose to terminate experiments when we felt we'd observed what was interesting to observe.
Right.
In simple terms. So I mean, it is, essentially arbitrary, but we would not. I mean, I would never, as someone who's interested in the way the world works, I would never terminate an experiment if I feel I still have something to learn from it. I mean, that's one of the really important things. I presume we'll talk later about the testing regime and testing regimes associated with cladding products. But that's one of the kind of key messages for me, overarching, relevant to the question about rivets versus cassettes and my comments about the SBI experiment. If you test an ACM-PE product in an SBI and you test it riveted and it achieves some level of performance and you stop the test, when you test a cassette and you achieve some level of performance and you stop the test, you're missing information when you stop that test. In particularly on the riveted system, you're missing the escalation. You're missing the shock and alarm of what these systems and products can do when they are pushed too far. And that is a problem with fire resistance testing, with standardized compliance testing. Is because you say these tests are run for 20 minutes. That means that people can manipulate their products to make it through the allotted time without you observing maybe something that you might like to observe if you really wanted to understand what was going to happen. So in our experiments, I mean, that's a very long-winded way, with apologies, of answering your question, but I do think it's an important insight, is that if you want to understand how a product burns, then you should let it burn until you can't learn anything anymore. And that's the criterion that we used.
Now, thank you. No, that's helpful. Now, looking at Grenfell itself, as we know, the fire there spread from immediately outside flat 16 to the crown in the 20-minute period. But taking all of the evidence into account that you've seen, is it your view, and to tell me if this is not the case, but is it your view that the contribution of the insulation products to the total energy released by the ACM PE cladding occurred after the local burnout of the fire of the ACM PE?
I mean, the interesting distinction in words here. I mean, I would, and again, I think the words that I've used in the report are imprecise. Local. I mean, I've used those words without defining what I mean by local burnout of the ACM. What I would mean by that is until there's no polyethylene burning anymore. But I think perhaps the more relevant question, or the better way of phrasing that, would be to say until local burnout of the cladding system, because in some cases you did have ongoing combustion of the insulation beyond the point in time where there was no obvious burning of the PE. It's quite hard when performing these experiments. It's quite hard to identify with absolute precision when there's no more PE burning. I think in the experiment that I showed last week, I think it was the experiment was at 21, I think. Where I showed the full progression of the experiment and highlighted some of the key moments, and I think that the moment that we observed the last burning of PE, and that was at around 18 minutes of the 20 minutes. Whether that is a consistent 18 minutes or whether sometimes it's 8 minutes and sometimes it's 26 minutes, I would have to go back and look at the data to know for sure. Right. But I don't think it's a hugely significant point, because at the end of the day, we're interested in how much energy is liberated by the cladding system, and we're also interested in the timescales over which that liberation of energy occurs.
But when you say cladding system in that answer, do you mean the ACM, or do you mean
I mean the external wall arrangement.
construct the build-up?
Yes.
Right. Now, I see. Is it? Can you just help me? Is it the case that energy released by the insulation products as part of that external wall build-up, after burnout of, or local burnout, if you like, of the PE ACM, was not relevant to the nature and speed of the spread of the fire at Grenfell?
Sorry, could you ask that again?
Yes. Well, let me try it differently. What was the contribution of the insulation at Grenfell Tower after local burnout of the PE?
I mean, I would say pretty minor. I mean, for the Celotex product, it stopped burning. Once the PE was gone, the Celotex wasn't really burning anymore. For the Kingspan product, the burning that was ongoing was much less severe, smoldering and a little bit of flaming. So yeah, I mean, I think not very significant would be. I mean, I'd struggle to put a percentage on it, but not very significant. Yeah.
Now, if we go please to page 127, I'll show you the paragraph. It's paragraph 685. But you say there that the experiments show that the arrangements using non-combustible mineral wool insulation grew to full involvement of the PE cord ACM more rapidly than for the foil-faced combustible insulation products. Now, in light of that conclusion, are you able to tell us whether the theoretical percentage contributions to total energy release attributable to different types of insulation products provides any kind of reliable indication of the relative contributions of those insulation products to the speed and extent of flame spread?
With apologies, could you give me the first part of that question?
Yeah. Given the conclusion that you've set out at 685, which is that non-combustible mineral wool insulation grows to full involvement of the ACM more rapidly than the foil-faced combustible insulation, given that conclusion, are you able to tell us whether the theoretical percentage contributions to total energy release provided by each individual insulation product provides any kind of reliable indication of those contributions to the overall speed and extent of flame spread, where you have a PE cord ACM system?
I think what it tells us is, as I said last week, I think what it tells us is that contribution in comparative terms is relatively minor, if it exists at all. I mean, obviously the insulation materials are pyrolyzing. They are liberating flammable pyrolysis products. Those products, in the presence of heat and oxygen, are going to burn, and so there is a contribution. I mean, you cannot. I mean, it would be very hard to argue that there is no contribution. That contribution is probably comparatively minor. But the other thing that, it's important not to oversimplify I understand the question, but it's important not to oversimplify the complexity of the heat transfer environment within the cavity and the complexity of the interactions between the ACM and whatever is facing the ACM, whether it's foil-faced, combustible or non-combustible, or without the foil insulation. And that's really nicely shown. And this was the biggest sort of head scratcher, if you like, for us when we performed these experiments. When you, I have to be careful to make sure I get this right. When we tested the system with mineral wool insulation and we added the foil, the escalation occurred more quickly. When we tested with the combustible insulation products and we added the foil, the escalation occurred less quickly. And that's because the extent to which the insulation products can liberate energy, the extent to which the surfaces of those products heat, the extent to which the surfaces of those products reflect or re-radiate energy, and the extent to which the surfaces of those products can be heated by convective rather than radiation, rather than radiative heating. The balance of all of those factors changes for each of those products. So saying for sure, it must have been the energy liberated by combustion is actually a very difficult thing to do. So it's not I mean, what I want to say is it's not that simple. It's actually very, very complicated.
Right.
But I do think it's fair to say that the contribution, as I said last week, that the contribution to the total energy release of the cladding system, the external wall arrangement, during the course of the 20-minute duration of our experiments, it's shown here in the graph that's on the screen. Given that the combustible insulations, the three leftmost sets of data, are not that dissimilar from the mineral data, that the contribution from burning is comparatively minor when you compare with some of the other factors, the insulation, for instance.
Now, if we go back to page 123, we saw this earlier, and looked at paragraph 655 and 656, and there they are. Is it right that the percentage contributions to total heat release that you've set out there in relation to each of those products, RS5000 and K15, are calculated by expressing the heat released by the insulating product at the end of the experiment at an assumed 100% combustion efficiency, which is divided, I think, by the experimentally measured heat release by the ACM and the insulant at the point of local burnout, which is earlier?
I'd have to scroll sort of up in the report to see, because we've made a number of comparisons in terms of some of those comparisons are based on the mass loss measured during the experiment. Some are based on the total mass measured at the end of the experiment. I think in this situation, we're talking about the total mass loss from the insulation products. So to back up a bit, before we ran the experiments, we measure the mass of the sheet of insulation that goes into the rig. So we weigh it. At the end of the experiment, we take that sheet of insulation off the rig, and we weigh it again. The difference is the mass loss.
Yes.
If you take that mass loss and you multiply it by the heat of combustion, you get the maximum conceivable amount of energy that will have been released by that product. And that maximum conceivable assumes that the combustion is 100% efficient. And I think that is the basis upon which these numbers given here in these specific paragraphs are calculated, yes.
Well, let me try and help you. If you go back a page, please, to page 122 on the right-hand side of the screen, you can see what the observations are that are the basis of figure 33 and the methodology you adopted there, just to remind you of what it was.
Yeah, so that'll be based on the full 20 minutes.
Yeah, yes. So the question is it the case that your calculations don't compare like for two reasons? But the first is that they mix different timescales. One is that you're measuring total mass loss over the full period of the test, but you're also measuring heat released by the ACM up to point of local burnout, which is earlier on.
I mean, we did do the two different things, yes, but I think here we're just presenting the 20-minute mass loss as a maximum conceivable value.
Right.
Yes.
Let me ask it slightly. Is there any material flaw in the assumptions where you are measuring heat release up to the point of burnout in relation to the ACM, but up to the end of the experiment through the mass loss in relation to the insulating products?
Okay, I think I see what's happening here. So I think that figure 33 is presenting the area underneath the heat release curve, if you like, for the experiments.
Yeah.
Whereas the numbers that we're discussing are based on the total mass loss from start to finish. And the question is, which of those is the fairer comparison, I think is the question.
Well,
and,
yes.
and the answer is that the total heat release in figure 33 is the fair question. It is when you take the mass of the insulation at the start of the experiment, you run your experiment, and then you take the mass at the end of the experiment, and then you assume that all of that mass resulted in liberation of energy, you are, if you like, being unfair to the insulation product, because it's not the case that all of the mass turns into energy, right? It is the case that the conditions in which that combustion is occurring are not those that would exist within a bomb calorimeter, which is where you get the heat of combustion from, where you have a 100% oxygen and you have the most efficient possible combustion environment. So now, how much less efficient the combustion environment in the cladding experiments that we ran is as compared to the bomb calorimeter, I can't say. But I do feel that I've been quite clear in the way that I've presented those data to caveat it by saying these are the maximum possible values we could ever expect. So this is sort of the worst case scenario. If we assume that all mass turns into energy, this is as bad as it could possibly be. In reality, it's going to be somewhat less than that.
Are you able to tell us whether the amount of mass lost between ACM burnout and the end of the experiment was material, was significant?
I mean, potentially, but only insofar as those are the words that I've used. With respect to what happens on a building, which is why we've done this, then as I sit here, I think probably in my report, if I had the opportunity to amend the report, I would simply change the words from until local burnout of the ACM to read until local burnout of the cladding.
Right.
And then it would be fine.
I see. So the answer is no, I think. There's no material.
In terms of my conclusions, no.
Right. And same question in relation to different combustion efficiencies, as between the ACMPE on the one hand and each of these combustion insulation products on the other. Are you not comparing like with like because you're mixing different combustion efficiencies?
Yeah, probably. Yeah.
And does that have an effect or impact on your conclusions?
No, because I don't think that my conclusions are based on calculations that assume 100% combustion efficiency. No, I don't think so.
Is it the case that if instead you did compare like for like by comparing the heat release contribution from the insulation using experimental combustion efficiency measurements at the same points in time, namely at peak HRR, peak heat release, that the percentage contribution in respect of the total heat release from the insulation components would be lower than you've said?
It's entirely possible. I'm not sure that that's a relevant question. I mean, we're not interested necessarily in just what happens up to peak heat release. We're interested in how much energy is liberated at that location, period. I mean, so it's not simply a question of what happens until we get to the peak. It's a question of what happens throughout the full duration of burning. So I think the answer is yes. It's possible that the contribution of the insulations up to that point might be less as a percentage rather than the numbers I've given. But I don't necessarily accept that that's an important question.
Now, if we go to page 35 of your report here, paragraph 239. We don't need to read it all. 239, I think, starts at the top of page 36. And you identify the middle of 236, and you identify the mineral wool insulation. And you say in the second sentence, the specific product chosen was a rock wool duct insulation lagging product marketed under the trade name Duct Slab. And I think it's right that was classified as Euro A1 and non-combustible under the national classification system, yes?
Yeah.
As far as you are aware, is that a foil face insulant?
Yes.
And marketed in the UK as a rain screen insulation product, yes?
I don't know if it's marketed as a rain screen insulation product. I don't, yeah. I mean, it doesn't really matter to me whether it's how it's marketed. What I'm interested in and what it is, I'm interested that it's a non-combustible mineral with a foil facer.
Right. Now, I want just to ask you one or two questions about 8414, we will come to the topic in more detail later. But in relation to the tests done under 8414 Part 1 carried out by the government following the Grenfell Tower fire, is it right to say that the nature and rate of flame spread on cladding systems incorporating foil-faced PIR and unfaced mineral fibre insulation behind PE cord ACM have been found to be comparable at large scale and at intermediate scale?
Could you run that past me again, with apologies?
Yes. Is it right to say, given the tests done under BS 8414 by the government after the Grenfell Tower fire in 2017, is it right to say that the nature and the rate of flame spread on cladding systems incorporating foil-faced PIR and unfaced mineral fibre insulation, both in each case together with a PE cord ACM rain screen, have been found to be comparable?
I mean, nature and rate, I don't know that we necessarily learn that much about the nature and rate from a BS 8414 test, which would be the basis upon which that question is posed, referring to the post-Grenfell DCLG tests, I presume.
Yes.
It is the case that in those tests that the system with mineral wool that the test with mineral wool was terminated at a similar time than the tests with polymer foam insulation. But I think, from memory, in those experiments, that the mineral wool was used without a foil facer. The polymer foam insulations had foil facers, so there's a mild distinction there.
Right. And is it right to say the same thing, that the nature and rate of flame spread on cladding systems incorporating foil-faced PIR, foil-faced phenolic, and unfaced mineral fibre insulation, in all cases with PE cord ACM rain screen, have been found to be comparable in modelling?
I mean, I'm aware that some modelling work has been performed, sponsored, I believe, by Kingspan. The veracity of that modelling and the extent to which that modelling has been validated, I think, is a question that I've not looked at in very much detail. I'm aware that the work has been done, and I'm aware that the conclusions of that work have been to suggest that there isn't a major difference. Professor Torero, in his report, has commented on that in some detail, and I think those would be very appropriate questions to ask him.
Right. Now, having regard to all the available evidence you've seen, including your own experiments, are you able to provide us with an opinion about whether the nature and speed of the spread of the fire at Grenfell Tower would have been materially different had unfaced mineral fibre insulation been used as the insulating product behind the PE ACM rain screen cladding instead of RS 5000 and K15?
I can only base an answer to that question on the evidence that I have from the experiments that I've performed. And as I said earlier today, my view is that the combustibility of the polymer foam insulations, which is effectively what this question is asking me, will have played a role that was probably something less than 10% of contribution to the escalation, the spread of that fire in an upward fire spread mode. Beyond that, it's very difficult for me to say one way or another. Yeah.
Thank you very much. Now, I'd like to turn next to a different topic and a different report, your Path to Grenfell report of the 10th of November 2021. And let's have that back up, please. That is at LBYP 2701. And I just want to turn to page 4 in that and run through the table of contents with you, where you set out the structure of your report. And we can see there that it's divided into 3 parts, each with references, and an Appendix A. Now, Part 1 is the purpose of testing, yes? And you set out there 3 categories of tests, explaining the differences between them and giving examples of fire safety tests in each category, yes?
Yes.
So Category 1, unrepresentative tests, Category 2, model tests, and Category 3, technological proof tests. And then Part 2, foot of the screen, the path to Grenfell, and that's drawing together the various narrative threads relating directly to fire safety testing, research and investigation, as well as building regulations and the various pieces of associated statutory and industry guidance. Yes?
Yes.
And just on that, is it right that you begin that part of your report with an overview of the development of the building regulatory environment in England and Wales starting in 1919, describing the deployment of particular fire safety tests within those regulations and the relevant guidance?
That's right.
Yes. And you also, I think, address a number of historic UK cladding fires on high-rise buildings, offering, I think, analysis not only of the fire events themselves, but subsequent investigations into those fires, such as Knowsley and Garnock.
To the extent that I was able to, yes.
Yes. And is it right that you also offer analyses of patterns of risk and vulnerabilities in fire safety, which existed at the time of the Grenfell Tower fire in June 2017, as revealed by these different narrative threads? Yes?
That was what I attempted to do, yes.
And you discuss a number of what you call missed opportunities, where the statutory guidance and regulatory compliance testing regime could have been made simpler or less permissive, I think.
Certainly, yeah.
Yes. And you've also got, if you turn the page, please, to page 5. It only goes on, actually, to part 3, closing remarks on page 7, and Appendix A on the same page, which starts at page 268, which is about regulatory capture. Yes?
Yes.
And if we turn very briefly to Appendix A at page 268, we can see that it's headed The Purpose and Evolution of Fire Safety Regulation. And if we go in that to 1641, paragraph 1641, at the beginning, you say, whilst I do not hold myself out as a social scientist or as holding any particular expertise in science and technology studies, STS, I have had a demonstrated academic interest in the roles of regulation and education in fire safety engineering, design, practice and enforcement for more than a decade. I've also published peer-reviewed papers in both areas, as noted in section 31. And if you look at 1644, you tell us that the evidence presented in this appendix also underpins some of my interpretation of the evidence that I present in parts 1 and 2 of this report. However, I've placed it in an appendix because I do not hold myself out as an independent expert in this area. So that's right, is it?
Yes.
And you then offer some, as we've seen, some closing remarks in part 3. Now, I'd like to start with part 1 if I can. And can we go, please, in that to page 13, paragraph 53. And we start with some simple propositions, I hope. You start, the purpose of testing is to allow an individual or an organisation to use the results of a test to make a claim about how a material, product or system will perform in a real in-service situation. And you say, if you go on in the same paragraph, a little lower down, tests can never exactly mimic operational use of a technology because test designers seek to minimize uncontrolled variables and introduce instrumentation that would not normally be present. The differences between a test and operational use means that, quotes, tests get engineers closer to the real world, but not all the way, close quotes. And that's a quotation from Pinch, 1993. And if we go to paragraph 54, you say, the key issue, therefore, is not whether a test is, quotes, realistic, close quotes, because it can never be completely so, but rather whether it is sufficiently, quotes, representative, close quotes. As Downer argues, quotations, since even the most realistic tests will always differ in some respects from the real thing, engineers must determine which differences are, quotes, significant, close quotes, and which are trivial, if they are to know that a test is relevant or representative. And you quote from Downer, 2007. Now, you use expressions there, but we'll come back to this point in relation to large-scale testing later, but can you explain in summary why it is the case that the question is not whether a test is realistic, but whether it's sufficiently representative?
Why is that a relevant point?
Yes. Why? Can you explain the distinction, reasons for your drawing it?
Well, because of what it says in the first line of that paragraph, which is that the purpose of testing is to allow an individual and organization to use the results to make a claim about how a material product will perform in a real in-service condition, and because one can never devise a standardized test that will reproduce exactly the end-use conditions of a product. That just, it's just not a practicable approach to testing. So one has to come up with a test that asks the questions that allow oneself to make a claim about how the in-service performance is going to be, recognizing that the test cannot reproduce reality. So designing tests that ask the right questions that are representative of the things that one wants to know about a product is the trick with these tests.
If we go to page 15, paragraph 64, you explain there as follows. Testing for fire safety needs to achieve two main purposes. First, and most importantly, it should enable regulation that achieves societal objectives with regard to safety. Second, it needs to be practical in operation, providing reasonably consistent results without being overly burdensome in cost and time. And then at 65, you say, the first of these purposes hinges on attaining a useful correspondence between test results and real-world performance. In principle, it doesn't matter whether a test is realistic so long as it is useful in this regard. Now, just pausing there, what do you mean by a useful correspondence with real-world performance, as distinct from a test which is realistic?
A test that tells you something that you can make use of in order to achieve satisfactory fire safety outcomes.
What's the difference between that and realism?
Well, realism is not practicable. That's the kind of compromise that I'm alluding to in this section. You can't have a test that would realistically that would simulate end-use conditions for every product.
I see.
So you have to have a test that tells you something useful. There's a nice expression about models, right? Which is that all models are wrong, but some models are useful. You could say something similar about fire tests. You could say, all fire tests are unrealistic, but some of them are useful.
I'll follow. Then let's go to page 19. And at the top of the page there, you identify, during the period 1932 to 2017, three categories of fire tests used within the regulatory system in place in that period. And you say that there are unrepresentative tests, model tests, and technological proof tests. Now, that taxonomy there, is that your own, or is it one that's articulated and recognised in the literature?
No, that's a local taxonomy, if you like. It's mine.
It's yours?
Well, mine along with colleagues who I was working with on this report. So Graham Spinardi, who I've mentioned in Appendix A. Yeah.
It's Grenfell specific, your work specific?
Correct.
I see.
Yeah.
Now, am I right to understand that it's important to understand the difference between these types of tests, the purpose of developing them, and what they were intended to measure or demonstrate in order to understand the limits of their credible use and application?
Yes. I think it's important to think about what these different types, which is why this taxonomy has been written down in this report. I think it's important to think about different types of tests, the basis upon which they were developed, how realistic or representative they are, and therefore what burden of responsibility lies with those people who use those tests.
And would it be right also to say that certain relevant fire safety tests in the UK were implemented and used in practice in the period before Grenfell in ways which did not align with the intention, the logic, and the limitations of the tests themselves?
That's my view, yes.
Yes. And we'll come to some specific examples of that shortly. But is the reason for that non-alignment regulatory influence? Is that one of your rationales?
I think by regulatory influence, you mean the influence of regulatory processes by industry, for instance, or?
Well, is it the case, it was a bit of a cryptic question perhaps, is it the case that because the deployment of these tests within statutory guidance and practice, specifically ADB, gave them a specific status that might have tempted people to ignore or perhaps misunderstand their applications?
I think the answer
their
is
limitations.
I think I would say yes to that. I think it's clear that that the way people were, it seems clear that the way people were thinking about what following the recommendations of approved document B was doing would indicate a misunderstanding of well, certainly this taxonomy of tests and the way that tests should be viewed. You know, for instance, the idea that one performs a BS8414 test, takes the data from the BS8414 test, has those data classified in accordance with BR135, and gets a free pass to use that combination of cladding products in any variation on any building, is in my view, a misconception of what that test is and what it's for and how it should be used.
Yes. Now, turning to the first category, therefore, unrepresentative tests, can you describe for us, in summary, the main properties or characteristics of unrepresentative tests?
These are tests that are typically very small, and they are tests that give you a piece of information which is used to try to make some claim, but which is essentially totally non-representative of an end-use condition, which is why I've called them unrepresentative tests. So they're tests where you ask a question. The way you ask the question is totally unrepresentative of any sort of real construction application.
Right. Now, if we go to page 29 in this report, and let's look together at paragraphs 140 to 143. Yeah, thank you. That's it. 140 to 143 there. You've set out the tests above that at paragraph 133, which we could just scroll up, we can see. You've got the BS476s and the BS ENs there, the oldest of which dates from 1970. And you've set out a list of characteristics at paragraphs 139 to 143 there. Are the tests that you list under that category those which deal with combustibility?
So part 4, part 11, 118, yes, they are.
Yes.
Yep.
Yes. And I think you then provide an overview of the history of the development of combustibility test methods at page 20, para 93, and you say that is you describe that as the potential of a material to burn. Is that correct?
Correct.
So that when you say combustibility, that's what you mean, is it?
In
the context
in
of
non-regulatory terms, yeah. Combustibility would mean yes, the potential of a material to burn. So in non-regulatory language, combustibility would be a material that can react with oxygen and thereby liberate energy in the form of heat and light. Strictly speaking. So anything that has a heat of combustion is, strictly speaking, combustible. Now, so combustibility is, if you like, an on-off switch. It either is or it isn't. In regulatory terms, the regulatory system chooses to blur that a bit and decide that some materials that have a very, very small amount of combustible content, i.e. content that could react with oxygen and release energy, can be deemed to be non-combustible. That doesn't make them non-combustible. It means they are deemed to be such.
Am I right to understand that by 2017 there were 4 independent test methods by which a manufacturer could demonstrate that a product was, quotes, non-combustible, close quotes?
Yeah, that would be referring to the 4 that are listed.
That's the 4 that are
here.
listed.
Yeah.
Then if we go on to page 23, or back to page 23 at paragraph 109, we don't need to read it all out because it's quite long, but is it right that you conclude from your review of the evolution of those various different test methods that both the definitions of, quotes, non-combustibility, close quotes, and the thresholds chosen for those definitions are arbitrary?
Yeah.
Yes. Can
Yeah.
you... Yes, and specifically, we go to page 24, paragraph 116. I think is it right that you explain that there? And in the third line you say, there is no particular reason why the criteria for flaming should be set at 0 seconds, 5 seconds, or 10 seconds. These are arbitrary decisions made typically by committee on the assumption that the precise value selected does not particularly matter with regard to the expected in-service fire safety outcomes.
That's right. Yeah. So what these I mean, I should probably say semi-arbitrary rather than arbitrary. These lines in the sand that get drawn on the permissible heat of combustion for a product to be, for a material to be considered non-combustible or limited combustibility. Those decisions get taken by committees of people who decide where those lines should be drawn under the assumption that something that would fall foul of those lines would burn too much, and something that would not burn too much. But those are judgments that are made by people. It's not a scientific truth, so to speak.
Now, in the third line, just before that sentence, you say at least partly arbitrary, and then you go on to identify the timing criteria for flaming. Are there any other criteria which you would say were arbitrary?
All of them. I mean, are at least partly arbitrary. So in the Part 4 and Part 11 tests, the chamber that the sample is lowered into is heated to 750 degrees Celsius. Why 750 degrees Celsius? Why not 600 or 900? And the answer is because they tried a bunch of different temperatures when they were developing the test, and they decided that 750 told them sort of what they wanted to know. Going to 900 was probably a bit difficult because it's quite hot to get something to 900. Going to 600 maybe didn't quite get things hot enough to observe the behaviors that you're interested in. So I mean, that's an example. The size of the samples, the shape of the samples, are they cuboid, are they cylindrical? If you look at the bomb calorimeter tests, the 1716, ISO 1716, for instance, and you look at where the Euro classes decide to draw the line between A1, A2, and B, those decisions were made by a committee of people sitting in conference rooms in Brussels deciding where that line should be drawn. So in that, insofar as these are committee decisions taken by individuals, they are arbitrary. They're not based on science, which is what I mean. They're not, as I said before, it's not a fundamental scientific truth. It's a decision that's taken.
I see. Yes, that's clear. Can we go then to 224 on page 45? Page 45, paragraph 224. And you say there, the non-representative tests were used largely as set out above. The thresholds were set at a conservative level. The tests were relatively sensitive to detecting the degree to which a material or product may or may not burn. However, the regulatory influence of this category of tests was limited as regards their application to combustible cladding materials and products. That last sentence, are you able to clarify what you mean there?
Well, if we're thinking about for instance, the Euro classification, the European classification system. So the European classification system uses ISO, the bomb calorimeter test and the drop test, similar to 476 Part 4 or 11, to define A1 and A2 classifications, which are the non-combustible, limited combustible classifications. Once you get down into B and lower down, B, C, D, E, those tests aren't relevant anymore because the products they're not non-combustible or limited combustible. So the differentiation between the combustible products is made not on the basis of the potential energy contribution on heat of combustion. It's made on the basis of their reaction to fire in an SPI predominantly. Yeah.
I follow. So you're really just focusing on the upper end of the scale in that sentence.
Yeah, I mean, what I'm trying to tease out there is that the heat of combustion is used to draw a line that those who drew the line considered to be, based on my assessment, I wasn't in the room, based on my assessment, quite a conservative line. A material that has a heat of combustion of less than 2 megajoules per kilogram, to use my sort of language from last week, is not a very burning material. And no matter what you do to that material, the amount of energy you're going to liberate is comparatively small. And so you could have drawn that line at 10 megajoules per kilogram or 30 megajoules per kilogram, but they didn't. They chose 2. And the reason is because they wanted a conservative line, despite the fact that they were acknowledging that they were allowing some contribution to burning, just very, very small.
Right. And you say that consideration doesn't apply once you're down into B, C, D, and
Yeah, I mean, you could have defined B, C, D, and E. You could have said, well, something can only be given a B if, in addition to achieving X and Y in the SBI test, it has a heat of combustion less than 15 or something. But they didn't do that, right? They set heat of combustion aside once they were down into the lower ratings.
And now let's turn then to the model tests, which is the second category of fire tests that you describe. Am I right to understand that small-scale model tests are modelled on and underpinned by larger-scale research based on on more realistic scenarios?
Typically, yeah. I mean, that's the way that I've outlined them here. Yes.
Is it right that those scenario tests are intended to be representative of real fire hazards which might be present in real buildings?
The models that are chosen as the basis for the model tests, yes.
And the measurements in those small-scale tests are intended to, is this right, to correlate with the outcomes observed in the more representative scenario tests?
That's right. The hope when developing a model test is that one takes a model that is relevant to the fire. So like the best example is the single burning item test in the European classification system. I mean, the BS 476 Part 6 fire propagation test is also a pretty good example. Both of those test methods, the classifications that drop out of them are linked to a fire burning in the corner of a room. So the model that is the scenario is the fire burning in the corner of a room. And then the hope is that you can make a test that doesn't require the burning of a fire in a room to infer what would happen if you use that product in a room with a fire in the corner, and then you don't have to burn a room every time you want to know the answer. You can do a BS 476 Part 6 test instead, and still differentiate between products in a way that is faithful to what would occur in the room.
Yes, and I think your report gives three tests which fall into that category: the BS 476 Part 6, BS 476 Part 7, and the SBI test. EN 13501 Part 1. Now, I think each of those tests have been described previously by the inquiry, to the inquiry by Dr. Lane and others, so we don't need to go through the methods or the apparatus or the associated classification systems. But I just want to ask you 1 or 2 specific questions. Is it right that, and I think it is right, that for all 3 sets of tests, they can only be strictly applied to products rather than materials, unless a product is homogeneous?
Strictly, yep.
Yeah, yes. Can you explain, and this may be a very basic question, but what is the difference between a product and a material?
I mean, that's quite I'm sure we could argue this point all day. When I think about it, it has to do with the homogeneity of the sample. A product is often going to be something that is made up from different materials. And in the context of this inquiry, the most important case would be like a flat layered product, like a foil-faced foam insulation or an ACM product. So if you take, for instance, foil-faced insulation, you've got a polymer foam, that is a material, and you've got aluminium foil facers, those are materials. Now, it's slightly muddy in that case because the foil facers, certainly of the Kingspan product, are not just foil. There's fibers and various other things in there. And so for an ACM product, the aluminium skins are a material. The core or filler is a material, polyethylene, and so the product is a composite. But you could have a product that is also a material. So a high pressure laminate cladding panel, which is uniform in composition throughout, homogeneous in composition throughout, is just the panel of a material, right?
Yes. Now, you say in your report that, and this is paragraph 178 on page 38, but You say that these tests can only be strictly applied to products. You use the word strictly there. Why is it that those tests are to apply to products strictly rather than materials? What's the basis for that?
Because what you're doing in the model test is trying to assess how products are going to perform in a model scenario, and what is relevant to the model scenario is not necessarily the material response, but is the product response. You know, it's you've developed a model of a room. The reason you've got a room with a fire in the corner is because you want to understand what's going to happen in rooms lined with that thing if there's a fire in the corner. Right? You want to understand how quickly that fire is going to grow and whether that fire is going to progress to flashover. So there's no point taking the core of an ACM and testing it on its own in a room corner test, because that's not representative of the end use condition. It's not sufficiently representative of the end use condition. It's not helping you answer the relevant question, if that makes any sense.
Yes, I see. But I'm really after the distinction between products and materials. Why do these tests only apply strictly to products and not to homogeneous materials?
I think because they're model tests, because they are tests that are supposed to be asking questions about performance of products in fire scenarios. In the scenario that you use to develop your test.
And we know that Part 6 says so. Part 6 of BS 476 actually says that it applies to products.
That's right.
And the logic, what is the logic, though? I know that it's a model test, but just to say that it's a model test explains why it only applies to products and not materials is somewhat circular. What's the underlying rationale for the distinction?
With respect to the Part 6 test, the underlying rationale, I mean, I don't know. Again, I wasn't there. I wasn't born yet when that Part 6 test was developed. I think in the 1950s originally. But the rationale, from my perspective, is that taking the Part 6 test as an example, the Part 6 test is asking questions about the ability of a product to contribute energy to a fire. So it's asking questions about the amount of energy that a product will liberate when heated in a compartment fire within a room, and about the timescales over which that occurs. Mr. Chairman, you look like you want to say something.
Well, it struck me listening to this exchange that maybe one ought to be thinking in terms that the test is only designed to be applied to products. It's a test that was conceived in order to test products. Would that be right?
I wasn't there, but that, based on my understanding of what the test is, what it does, and the questions it asks and answers, I would agree with that, certainly.
And I think Mr. Millett's question was perhaps slightly tempered by the fact that you used the words can only be applied to products. I mean,
Okay.
It can be applied to any material that you choose to apply it to, I assume. So
Go for it. Yeah.
wood, for example, or even a PIR insulation board without any foil facer, you could put through this test, couldn't you?
You could put.
That would be an homogeneous product.
Yeah. I mean, certainly you could put anything you like through the test.
Yeah.
Yes, absolutely. Whether putting that thing through the test makes sense in terms of the questions you want answers to,
Quite.
and in terms of the regulatory outcomes that
Yeah.
would eventuate, is maybe a secondary question.
Quite.
But I mean, I think where I was going in my answer to Mr. Millett was to say that the reason that I think these products can only strictly or credibly be applied, or to these tests can only strictly or credibly be applied to products, in the case of the Part 6 test, is that if one is interested in understanding the contribution of a product to a fire in a room, the perfect example is within the evidence to this inquiry, that, for instance, there were insulation manufacturers, Kingspan, who were performing BS 476 Part 6 tests on the foil facers alone, with some notion that getting a Class O rating for the foil facer meant that the product with an underlying insulation would be Class O. And that is just utterly absurd because, I mean, not least because the facer has perforations in it, but because the underlying foam insulation will contribute to the fire that you get in a room, which is the model scenario that you're interested in assessing. So to test the foil facer on its own is just completely and utterly nonsensical and you know, could never be defended in my view. So that, I mean, that's sort of why I say that. It's so that we don't get situations like people testing foil facers on their own and claiming that that tells them something useful about the reaction to fire of a product. Unless, of course, you're selling foil.
Now, just picking up your example, which I think is one you've used in your report, actually, at page 180, at paragraph 994. Let's go to para 995, where you say this. Bearing in mind the logic of the third way, it is my understanding that tests might be undertaken in this way in order that a claim could be made that the surface of the K15 was class 0, despite the fact that the product as a whole was not. Such an approach would allow Kingspan to generate the appearance of a product being class 0 and thereby generate the appearance of compliance with approved document B, and hence the appearance of compliance with paragraph B4 of the building regulations. I note that I would consider this practice to be utterly indefensible, both by any manufacturer and or by any compliance testing laboratory who knowingly undertook and reported such testing. And then you have a footnote at 537. In my opinion, the BS 476 Part 6 testing standard is absolutely clear, you say in italics, absolutely clear that the Part 6 test method is to be used to assess the fire propagation performance of, quotes, products, or italics, products. I am not aware that Kingspan sell aluminium foil facers on their own as distinct products for the construction industry. And then if we turn the page, please, to the foot of page 81. And so I do not understand how either Kingspan or any competent testing laboratory could undertake BS 476 Part 6 testing on this basis. I am aware of the view approved document B could be interpreted so as to indicate that, quotes, the surface of any composite product, close quotes, can be assessed independently of the rest of the composite product. I consider any such claim to be patently absurd. In discussing the test specimens to be used in BS 476 Part 6, the testing standard explicitly states that, quotes, 4.2.2 products of normal thickness 50 millimetres or less shall be used to full thickness, and, quotes, 4.2.3 for products of normal thickness greater than 50 millimetres. The specimen should be obtained by cutting away the unexposed face of the product to reduce the thickness to 50 plus 0.3 millimetres. The product, in this case, is Kingspan K15 foil face phenolic foam insulation, and so I consider it self-evident that the foil facer must be tested alongside a phenolic foam backing. You go on to say, with measurements, regardless of the specific definition of class 0 given in approved document B. Now, that's a long footnote addressing a potential interpretation of the regulations and approved document B. Is your reasoning based on your scientific experience, or just on a reading of the language?
My reasoning for what? For the assertion
view.
that it's absurd to test the foil facer alone?
Correct.
I mean, I would argue that you don't need much experience to make that assertion. Frankly, I mean, as you can sense from the language I've used here, when I discovered that this was going on, I was absolutely incredulous. I could not believe that this was going on. I refused to believe that it was happening until I saw the evidence. Yeah, I mean, I guess it's based on my technical knowledge, but I think, to me, it's plainly obvious that you just can't do that.
Now, am I right to understand that for all three of the model tests, BS 476 Part 6 and 7 and the SBI tests, there are 4 of them, I think, in total, actually, which you talk about in this part of your report, the real fire relevance, the reference scenario, is a fire growing inside a compartment or a room or a corridor within a building.
That's right.
Not an external wall.
Correct.
Now, we know that national class naught, achieved by a combination of results from tests carried out under Part 6 and 7 of BS 476, or after 2002 Euroclass, the Euroclass regime, were the classifications recommended in ADB for external walls over 18 metres in height. Do you know why?
Do I know why?
Do you know why, or do you know the rationale for using Class 0 as a classification regime, or Class B as a classification standard for an external wall, given the reference scenario was a fire inside a room or a corridor?
No, I don't know why. I mean, it's a very important question, and I'm a bit surprised that I have to say no. I don't know why. I mean, I know why the tests came into existence, and I know how they came into existence, and I know the structures of the committees and the experimental underpinning research and all of those things. Why Class 0 was able to persist, let's say, for so long within the English regulatory system, I don't know. I mean, I have some views, I presume we'll talk, which I've intimated about in this report, but no. And with respect to the European classification system, in the development of the European classification system, from the late 1980s through until 2002, when they became when they were inserted into the approved document B, based on my understanding of what was going on in those years, there was an understanding, or at least a hope, that a classification system for products that was based on different reference scenarios that would be relevant to external cladding would also, that would occur. An activity would be undertaken in order to define a classification of products that would be more relevant to a reference scenario involving external cladding, but that never occurred. Why that never occurred is a very important question, and I don't know the answer to it.
Right. Thank you. Let's go to page 39 of your report then, paragraph 193. You start at 189 by identifying three important conclusions which can be drawn from the development of the model fire tests. First, you say they were created on the basis of underpinning research and a body of knowledge. Second, the classification thresholds were essentially arbitrary in terms of fire safety outcomes. And then third, all of the tests were developed on the basis that the relevant hazard was a fire growing inside a room or corridor. And then at 193 you say, none of the above test standards was designed or originally intended to represent the fire hazards that might be presented by a fire impinging on the external cladding of a building or its potential for escalation. The reference scenario, quotes unquotes, was and is far removed from the circumstances of a cladding fire potentially resulting in promotion of external fire spread. And my question, showing you all of that, is this: why does that matter?
Why does it matter? It matters because the physics that we are interested in, that govern the way a fire grows and spreads on the outside of a building, are very different than those that would be experienced inside a room. I mean, to give you one example, all of those tests that I've discussed previously, the maximum heat fluxes to which the product samples would be exposed would be considerably less than we would expect in a cladding fire scenario if you have a fully developed fire venting from a compartment. So the products are not exposed to representative heat fluxes, would be just one example of one of the differences. But the scale, the mechanical issues, Professor Torero, I think, outlined a whole host of reasons why cladding systems are complicated in his presentation last week, and all of those factors are relevant. I would also just add that Mr. Millett, have also noticed that the screens have gone blank.
Yes.
There's mild confusion.
I wasn't going to stop you.
But I mean, I think it's also worth noting that it's important for me to say that just because a test is based on a model scenario that is not the scenario that you're interested in doesn't mean that the test has no value. It's not that BS 476 Part 6, Part 7 SPI tests tell you absolutely nothing of interest. They have the potential to tell us lots of interesting things about the way products behave when they are exposed to fire. But they're not asking the question in a way that is immediately relevant to the scenario that we're interested in. And to me, which is what I would say about all experiments or test methods rather, what's important is not criticizing this test or that test because it uses a different model scenario. But how are people using the outcomes of these tests? How are people understanding the questions that these tests are asking? How are they using their understanding of how these tests are performed and their understanding of the outcomes to make decisions about what is okay or what is not okay on the outside of a building? So it's about, we have a mantra in my research group at Edinburgh, which is, the test is the test. It's what people do with the test that is worthy of our scrutiny, or more worthy of our scrutiny. So I wouldn't want to get too hung up on that reference scenario business. It's important to be aware of it, and it's important for the people who use the tests to be aware of it. But it doesn't mean that the tests are useless. So I would be quite careful about saying that.
No, understood. Let's see if I can just explore this just a little bit more. Can we go, please, to page 174 and go in that to paragraph 958 there. You say the reference scenario for the European and notably also the national material product classifications is a room with the materials/products in question used as internal linings. By contrast, the relevant scenario for vertical fire spread on the external wall, as notionally represented by BS 8414 or similar testing, is the impingement of the plume from an already large fire on the external cladding. And then you say this in italics. These two scenarios represent fundamentally different thermal and mechanical conditions to the exposed materials/products. Now, you say they're fundamentally different. The question is whether those fundamental differences matter. In other words, does the fact that the Class 0 or SBI tests might tell you something, does it matter that they are telling you something in the context of the application of the relevant product to the external wall build-up as opposed to a room?
Yes, it does matter. But what matters is not that it's different. What matters is that the person who is using what is observed, the outcome, thinks about the extent to which the differences might matter, given that they're going to use that result for some other purpose. If that makes sense. It's maybe quite a mild distinction.
But isn't that partly because the circumstances in which the test is carried out brings with it a host of undefined factors which do actually have a bear on the outcome? So if you light a fire on the inside of a building, in a room, you've got various factors in play, and a fire on the outside is subject to different factors. So you're not actually going to be comparing the same things, are you?
Absolutely, and what's important from my perspective is that the people, the practitioners who are using these tests, have some understanding of that, have some understanding of what, where did this test come from? I mean, to give you the example of the tests on foil facers and my disbelief that was going on. I immediately sort of asked myself, who on earth was running these tests? Who on earth was performing tests on foil facer stapled to calcium silicate board on behalf of Kingspan and didn't know to ask the question, what are you guys doing? This is not appropriate. And who signed these reports off? recognizing what was going on, and didn't say, well, hang on, this is not appropriate. You cannot be doing this, right? And I'm still not sure I know the answers to those questions, but that's the issue. The issue is not that a BS 476 test is never useful. The issue is that somebody somewhere within this process of building regulation and oversight needs to be the person who stands up and says, no, this is not okay. We cannot be doing tests like this. And that didn't happen. And that's the issue.
Just going to the differences, though, do the fundamental differences between the thermal and mechanical conditions for a room corner test, SBI, or the 476 Part 6 and 7 tests on the one hand, and the use of the product on the external wall of a high-rise building, did they go so far as to invalidate the assumptions of the underlying research and reference scenario? In other words, did the fact that the product was going to be used on the external wall of a high-rise building mean that the differences between its application there and the circumstances in which it was tested were so fundamentally different that the assumptions underpinning the test were inapplicable?
I mean, I think the assumptions... I mean, I can only answer this question in a more general way. I don't believe that it is ever okay to blindly apply the results of a compliance test. So if someone wants to take results from a test that was developed on the basis of a fire burning within a room, and they want to take the product assessed on that basis and put it on the outside of a building, then yes, they absolutely must think about the ways in which their application of the product might differ from the test scenario in which it was evaluated. And yes, if you're going to use a product that is tested on the inside of a room with a small fire burning in a corner, and then you say, okay, well, now I'm interested in how that product is going to react when it's vertically oriented on the outside of a building and exposed to a plume from a post-flashover compartment fire. Very, very different scenarios. And yes, you better think very hard about whether the assessment from the room corner test or the model that's based on the room corner test is relevant. And probably it's not in a bunch of ways.
I have one question flowing from that, Mr. Chairman. May I ask it before I call for the break?
All right, Mr. Millett.
What is there in approved document B when it presents Class 0 as the applicable classification standard, or Class B for the applicable classification standard in diagram 40, which tells you, the building designer, that you have to ask yourself those questions?
In approved document B, I mean, off the top of my head, now you've asked the question, I'd want to go back and read through approved document B. I can't point to a specific clause that says that. But I don't necessarily believe that approved document B is obliged to say it.
That's another matter. But thank you, Professor. Mr. Chairman, is now a convenient moment for the break.
Yes, I think it is, Mr. Millett. Thank you very much. We'll break there so we can all get some lunch, Professor. We'll come back, please, at 2:05. And usual thing, discuss your evidence with anyone while you're out of the room.
Thank you.
Thank you very much. Thank you, Mr. Millett. 2:05, please.